All right, good morning. Let's get started. Welcome to the session on parallel and asynchronous programming with streams and completable futures. My name is Venkat Subramaniam. Let's talk a little bit about what we're going to do here. We're going to divide this into about two 90-minute sessions. So the first part, I'll talk about parallel streams, and we'll look at several examples. In the second part, we'll talk about completable futures, and between those two parts, we'll take about a 90 minutes break. We got a lot of stuff I want to really look at in terms of parallel streams and also in terms of the completable futures. So let's get started. Best time to ask questions or make comments is whenever you have it. So please don't hesitate to ask questions, make comments. Usually I just talk about stuff, write live code. So when you have questions, I will write more examples. So make it as interactive as you can. I'll be delighted to listen to your questions or comments, and then we'll move forward. So let's get started. We're going to talk about just a little bit about parallel versus asynchronous. What does one mean versus the other? Then we'll jump into parallel streams, talk about parallel streams, look at some concerns, how to use some of the variations. What are some of the concerns, when to use it, when not to use it, how to use it. So we'll take a look at a lot of stuff around that. And then we'll talk about, so that's basically where we're going to talk about parallel streams. And then once we finish that part, we'll talk about completable futures. And then we'll talk about when to use that, how to use it, what are some of the ways to approach using it. And also we'll take a look at some of the APIs. I found some of them to be very confusing in the beginning, but stepping back and looking at what they really mean can help us to understand how to make really good use of it. That's what we're going to do. So, and then, give or take 15 more minutes we have on hand, we can do Q&A or wrap it up depending on what we do. So let's get started. The very first thing I want to start talking about is when do we really think about parallel versus asynchronous? Well, I come from the world of programming in traditional languages like C++ and way back in time VB, and then moving on to languages like Java and C#. So mostly I've been used to sequential programming or synchronous programming. And when it comes to parallelism, it is something I got introduced a few decades ago. And generally speaking, languages like C++, Java, C#, we predominantly did parallel programming. The first time I really got exposed to asynchrony, I would say, is when I started programming on the Node and when I started programming with JavaScript. And I have to be honest about it, it took actually a little bit of effort to really think asynchronously, mainly because my mind is wired to think sequentially, my mind is wired to think in parallel programming, but asynchrony was something that really took a little while to catch on for me. But I want to talk about, what does it really mean to do something in parallel versus what does it really mean to do something in asynchrony? And it's not an easy answer, in my opinion, because, we think of threads when we think of parallelism. We think of threads when we think of asynchrony. Well, if both of them have threads in it, then what does it really mean to do things asynchronous versus what does it mean to do things in parallel? So I'll try to come up with a really silly example so we can actually maybe relate to it. Let's say we want to start a party. And of course, we can't have a party without pizza. What kind of party would that be? So we want to really have pizza. We want to also have drink in the party. But of course, we can't start a party maybe without drinks and pizza. Well, we could be a real sequential, boring life where you go out and get pizza and then you go out to get the drink. And most people have really left the party already because they're sitting there, waiting for food. So let's maybe think about this a little differently. So when we can use parallel is, you call two of your friends and say, hey, why don't you go get pizza? Why don't you go get drink? And then, of course, you wait for the pizza and the drink to arrive. The good news is, if it takes so much amount of time to get the pizza and so much time to get the drink, you're not going to wait for that much of duration doing it sequentially. You're going to do it in parallel. Well, maybe it takes a little longer to get the pizza than to get the drink, but as soon as both of them arrive, you are ready to get your party started. That's kind of like parallel. So you fork and then you join and you continue. So you're doing the two actions in parallel. Getting the pizza is going on while you're getting the drink, and when both of them arrive, you can start your party. Well, that's kind of like parallelism, where you do things in parallel or concurrently, and then of course, when the results arrive, you're ready to move on to your next step, which is to get going with the party. But you could argue to say, well, party is not about pizza after all. Party is not about drink. Party is about getting together and having fun. So why don't we think of asynchrony instead? So you ask one of your buddies to go get pizza, you ask one of your buddies to go get drink, but you get the party started. You're having good time chatting with people, turn on the music, and then maybe the drink arrives. Well, when the drink arrives, you don't have to wait for anything. You can start drinking. And then, of course, when pizza arrives, you can start eating it as well and have more drinks along the way. So in other words, in the asynchronous programming, you do set off things to run asynchronously, meaning you're not waiting for it to start or to complete. But when the result does arrive, you move on to do other things with it. There is no specific synchronization involved in asynchronous programming. Well, then how do you really do certain tasks when that particular operation actually completes? And the answer to that is typically use a callback to be able to receive the response when something is over, and in the callback you go off to do other things. But of course, callbacks do have other problems, and that's what we'll talk about Completable Future and see how that actually solves that particular problem. So we'll talk about that a little later on in the presentation. So for the first 90 minutes that we have on our hand approximately, we'll talk about parallel streams, dig into details of when to use it, how to use it, and talk about some of the variations with it. I don't really have any examples for you to try right now because we got a lot of stuff to cover, but I encourage you to take notes along the way. And if you do have any questions, I'll be more than happy to dive into. Or if you say, hey, let's explore some other aspects of it, I'll be more than happy to go into that as well, so we can do that accordingly. So let's talk about, in general, about, first of all, streams to begin with. I do have to say that this is one of the things that truly convinced me that Java is pretty exciting one more time. If you have ever listened to one of my talks in the, maybe about in the 2007 timeframe, 2008 timeframe, I was one of those guys on the other side of the picket line constantly complaining that Java sucks. And for me to be even here today and talk about the praises of Java is because that made a difference in streams. I wrote the very first book on Java 8. The book was released the day Java 8 was released. But one of the things I wrote in the book, my editor called me and said, are you serious you want to write something like this in a technical book? And I said, look, I live in Colorado, I said. And my editor said, okay, I'll give you that, and hung up. What I wrote in the book was, I said that the lambdas are the gateway drug, but streams are the real addiction. Not that I want to do anything about the drug culture in Colorado, but the point really is, I do really mean that. It is that lambdas are the gateway drug, but streams are the real addiction, meaning you kind of get excited about lambdas, you get excited about functional programming, but the real power of programming in Java is really in streams. And that's what really hooked me on to Java 8 and to Java itself, in my opinion, is because when I looked at streams and the behavior of streams, I was absolutely convinced this is phenomenal. So what does it really offer? Well, Martin Fowler talks about it. If you Google for this, you will find it. And Martin Fowler talks about this as what he calls as the collection pipeline pattern. And a collection pipeline pattern is a very vibrant way of looking at how we're going to start writing code moving into the future. For example, let's say for a minute, we are interested in taking a list of numbers, and we want to say, find the double of, let's say, find the total of double of even numbers. Well, in the imperative style of programming, what we would do is we will start with, let's say, a total is equal to 0. We want to output the value of total when we are done, but we would start with something like for int element coming from, let's say, numbers, and then we would pretty much at this point say, we are interested in if element mod 2 is equal to 0, which is an even number, then we would say total plus equal to the element times 2, and then we would loop through this and execute the results for what we are looking for. So this is saying that loop through every element in the collection, look for only the even numbers, and when you find the even number, double it, and then add it to the total. Well, that's the imperative style of programming, and we've been using things like for loops and breaks and continues all along the lines. But thankfully, moving forward, we can use the functional style of programming, and this is where what we are getting really is the so-called functional composition. And functional composition is probably one of the most exciting parts of functional programming, where what we can say here is we can say, given the numbers we have, we can get a stream. So what in the world is a stream? A stream becomes what's called the internal iterator. It's an internal iterator as in, this being the external iterator, you control the iteration with things like continue and break. An internal iterator is on an autopilot. You simply say go iterate. You focus on what to do per element, not on the iteration itself, and that goes on autopilot. So here we say filter given an element mod 2 is equal to 0, and then we map this value to the double of the value, and then we can perform a sum operation on it to get the final result of this particular computation. And this becomes the so-called the collection pipeline pattern, as Martin Fowler calls it. So functional composition becomes the collection pipeline we can use. So the collection pipeline has a clear benefit, and that is one of the reasons I get excited about functional style of programming is, well, I spent decades programming in imperative style of programming. I spent my youth programming in imperative style, and it took me a long time to realize that imperative style of programming that we've been using so predominantly imperative style has accidental complexity. And this is something that took me a while to really know and believe. But then I realized I've been using a fairly complex programming model all my life to program. Like I said, I spent my youth programming in imperative style. What I'm telling you is I had a terrible childhood. All I had to do was program in this poor model. And once I realized it, I then realized that functional style has less complexity overall, and that is one of the biggest benefits we get out of this. And if you look at the code here, this becomes really easy to follow, and we can go through a single pass through this. Given a collection of numbers, give me only the even numbers, but double the values that are even, and total them, and the code begins to read like the problem statement. That is one of the biggest benefits. But for our purpose here, another big benefit of this is not only does it have less accidental complexity, but it is also easier to parallelize. And this is another really big benefit of functional style of programming is it's easier to parallelize as well. If you had written a code like this before, where you had written code with imperative style of programming, imagine you wrote these kinds of for loops all through your code, and you have tons and tons of these for loops. And everything is going really well in projects as usual. But a month before the release, somebody comes to you and says, we got a problem. Our performance is really bad. We need to improve it. And you're struggling really hard night and day trying to improve the performance. You don't know how to really improve it. And then suddenly somebody tells you, I got a great idea. Why don't we use multiple threads? And usually that's not a great idea, because the minute somebody says that, your past experience, your past project comes to mind, because you remember what happened on the previous project you worked on. Everybody came to work, they smiled at each other, they had a good time, you went to lunch as a team, and everything happened before you started using multiple threads. And the minute you introduced multiple threads on the project, nobody liked each other. You stayed home, you stayed at work late in the night debugging code, and one night you just lost it. While you were debugging the code, you applied for the other job. That's called concurrency. And you realize this is not the way you want to spend your life, so anytime somebody suggests to use multiple threads, you're not too happy with it. Well, the reason for that is really clear, and as a result, I call that model as the synchronize and suffer model. And that's what happens. You start synchronizing and you start suffering after that, because it's incredibly difficult to really maintain code with all these locks and things you have to do, and that becomes to no end a period of debugging, and while you're trying to squeeze out performance, it becomes enormously complex. On the other hand, the beauty of the functional style of programming is, because you're honoring some good functional style of programming principles, which is to write functions that are actually pure. So because lambdas are expected to be pure functions, we can parallelize this code very effectively. That's one of the biggest benefits we're going to get out of this. Let's explore that thought really quickly here for an example, so to see how that's going to really help us to make that work. So we talked about from imperative functional style of programming, we talked about the benefits of the functional pipeline, less complexity, easy to parallelize, among other things. But I call this as parallel as a master switch. I call it a master switch because the people who created this are very smart. They made it so easy to do, and they just stopped shy of actually doing it. Oftentimes people ask me, if it is so easy to do, why didn't they do it? Why didn't they make everything parallel? Well, because they're very smart, that's why. Because they know that not everything is parallelizable. They know that making it parallel is opening a can of worms. They don't want to really do that unless we know really that's what we should be doing. So this is why I call it a master switch. It's a master switch because it is something you can flip, but the little fine print next to it is called the word think, meaning make sure you really want to do this because it's easy to turn on the switch, but you got to bear the consequences once you turn on that switch. That is something for us to keep in mind. So let's talk about execution sequence here, the sequential versus the parallel execution using the streams, and say how we can actually do this. So going back to this little example right here, let's talk about, let's say, a list of numbers one more time. But this time I want to simply transform these numbers, let's say. So I'm going to say numbers.stream. And then in this case, I'm going to say map, and let's say this is going to be a transform method I'm going to call. So given an element, I'll call transform, and in this case, I'll just pass the element to transform, and then for each, we'll simply say system.out.println, and then we'll just print it. Now, in this example, though, we're going to execute the transform method. Let's take a look at what the transform method is going to do. I'm going to keep it extremely trivial so that we don't spend too much time figuring out what the code is doing. So we will simply return, for really no good purpose, the number time once. It's really not doing much transformation at all, except that I'm going to call a sleep method right here of about a second delay. So let's say this is computationally intensive. It's going to take a little bit of time to execute, and I'm going to have this little sleep function that we're going to use to provide that little sleep along the way. So I'm going to run this little code, and as you can see, this is pretty sequential in execution. So what is it going to take? How much time is it going to take to run? Let's go ahead and just run this. We can easily see this. You can see that it takes about a second to run every single value. So clearly that sequential execution, really not something hard to find out. So at every single second, we get an output value from this collection. That's a sequential execution. But if I want to run this parallel, I said this is a master switch. There are two different ways to make it really run in parallel. The first approach is, if you are the creator of the stream, you can simply say parallel stream right here to execute it. So in this case, of course, it's a parallel stream. Now notice I did not do anything different in the, so this is one of the aha moments for me, is when you take a imperative style code, which is so beautiful, easy to understand, easy to follow mostly, and then you make it concurrent. That moment in time is when this innocent looking code turns into a monster, and nobody can identify and recognize it. If you worked on a project, you went away for a few months, came back, and you look at this and say, what happened to this project? Like a tornado ripped through it, because the code structure is extremely different. This is one of the things to keep in mind is in imperative style code. So imperative style, the structure of sequential code is very different from the structure of concurrent code. This is something we have suffered through a very long time in programming history. The structure of code is very different between concurrent programming and sequential programming, so much so that if you put your effort to really write the code and debug it and verify it, and the minute you throw concurrency into it, your clock resets, you got to start over again, because there's no guarantee that this code is exactly going to do the same thing, because the code is so different than what we started with. But the beautiful thing about the Streams API is using streams, one of the biggest benefits is the structure of the structure of the sequential code is identical to the structure of concurrent code. And this is a huge benefit when it comes to reasoning the code, maintaining the code, the ability to test the code as well. Those things make a huge difference. I was working on a project where we have an application that takes a very long time to run. When I say very long time, I'm talking about days to run, not minutes and hours. It's a huge math problem. We have to crunch literally millions of data, and it takes a couple of days to run. When I got invited on the project, the code was completely the imperative sequential style of programming. And what my client did was they took a very small sample of the project, which took only 12 minutes to run, and said, I've nailed it down to 12 minutes. We can't wait for days to see if our efforts really are working. So we took a very small sample of the project. It takes 12 minutes to run. Go for it. It took us 7 hours of rewriting that part of code to go from imperative style to functional style using streams. And at the end of the 7 hours, we ran the code again. And what took 12 minutes to run now took exactly 12 minutes to run. And my client said, good job, Venkat. That was 7 hours of effort. And the code is now functional in style. And he was a very positive person. He said, I'm really glad it doesn't perform any poorly. And then I said, well, thanks for that feedback. Awesome. And then I said, take the word stream that we had, and I said, turn that into parallel. And we just made it parallel, reran it. What took 12 minutes to run took less than 4 minutes to run. And that is the beauty of it. Without almost no effort, after all that effort, we were able to take the sequential code and turn it into parallel. And then, of course, then we said, okay, that's a great proof of concept. We're getting performance out of it. Let's go for it. And then, of course, we spent the next year working on this big project to convert everything from imperative style to functional style because we are getting the benefit out of it. The challenge really was where we had a lot of mutability in code. Because when you have mutability and parallel don't go together. You cannot mix them. There are several days I would go to work and my good colleague would look at me and say, the code ran really fast. And I would smile at him and said, and gave you the wrong results, didn't it? And he's like, yep. And then we'll spend the next 2 hours figuring out where the mutability was and remove it so we can get the performance and the correctness out of the code. So that is the challenge we have to really work through. So one of the biggest benefits, like I said, I cannot just underestimate this, is truly this is phenomenal. And that is when you use streams, the structure of sequential code is identical to the structure of concurrent code, and there is a huge merit for it. Because then truly the concurrency becomes the master switch where by a little toggle of a switch, you can get concurrency out of it. Now, this is one way to execute it. As you can see in this particular example, running it sequentially, you can see that it's running one at a time, as we can see right there. But on the other hand, if I were to simply change it as a parallel stream, then of course, we are going to, with almost no effort at all, we are able to run that code in parallel. As you can see, it did not take the time to run one at a time, a 1 second delay almost after we got the result right off the bat, and that's exactly what we are seeing with the parallel stream. So that is one way to really do this. On the other hand, of course, what if you don't have the ability to create the stream all by yourself? As an example, let's say you have a function, something along these lines, where you have a static void use. And this takes a stream of, let's say, integer, we'll call it stream. And in this case, it's going to go through the stream and do the printing of the data. So in this case, I'm going to start with the stream.stream. So let's bring in the stream API right here. And in this case, of course, the use method says stream, and on the stream, it is going to perform the map operation and the for each. Now in this example, I'm going to call useStream, use and then pass numbers.stream, and I'm going to pass that over to that particular piece of code. Now clearly this is going to run sequentially again like it did before, one step at a time, so that's really nothing unexpected. On the other hand, though, in this case, what if I were to want to make this run in parallel? Well, clearly, I am not the creator of the stream, so what am I going to do to run this in parallel? Well, then you can simply say .parallel right here, and as a result, this is going to now run in parallel. So rather than calling the parallel stream, you can also call the parallel method to run the entire stream in parallel. So if you're at the source of the stream, use the word method parallel stream. If you're not at the source of the stream, but you're somewhere after the stream has been created, you can use the parallel function to run it in parallel. As you can see in this case, when I run the code, you can see that it's running in parallel again, as you can see. So that's another way to do this. But a word of caution, however, this is something we have to be very careful about. You may wonder if there's a function called parallel, if there's a function called sequential, and it turns out, unfortunately, there is. So you can also run it sequential like this. So in this case, when I run the code, absolutely it runs sequentially as you would expect. But if you go back over here and say parallel stream, and then of course if you go back and run the code one more time, even though we created a parallel stream, notice it is running sequentially because you created a parallel stream, but you're asking it to be run in sequential mode. But what is even more important to keep in mind is, if you had said parallel right here, but on the other hand, if you said sequential right here, now, it's really hard to really imagine this, because naively, we may look at this code and say, aha, this is wonderful. This map will run in parallel, but the for each will run in sequential mode. Unfortunately, that's not the case. In this particular case, the very last one wins. So this is going to affect the behavior of the entire pipeline. So in other words, this is no op really because of the sequential below. So in other words, just because you make something parallel doesn't mean it runs parallel. The very last one is going to win. So it doesn't matter whether you had sequential or parallel along the way. So the question is, what does the last one really mean in this context? The word last one means the one before the terminal operation. So there are two kinds of operations that streams normally have. Those that are called intermediate operations and those that are called terminal operations. Intermediate operations are lazy. They get postponed evaluation until you hit a terminal operation. So the terminal operation is the decisive factor, and anything you do before the terminal operation, the last one rules. So if the last call was sequential before the terminal, then that's going to be taking over. If the last call before the terminal was parallel, that takes over. So in other words, you walk backward from the terminal operation and you look for sequential or parallel. Whichever you hit first, that's going to be the deciding factor going backwards from the terminal operation. That's what is going to take root. So as you can see in here, even though we said parallel and then we said sequential, when you run the code, it is all going to run sequentially. Of course, in this case, it wouldn't really make sense to see it unless we see when the transform is called. So let me go back to the transform, and I'm going to simply say over here, output, let's say called for, let's say number. Now notice in this case, it's running in parallel. So when I run this, you can see it ran in parallel, as you can see right there. On the other hand, if I said sequential, even though that's sandwiched between parallel and sequential, you can see that it's actually running sequentially, and that is because of the sequential taking effect, something you have to be very careful about. The streams in Java 8 do not have segments for parallel versus sequential. If you will allow me to digress for just a minute, I want to just compare this to something else, as it is pretty useful because a lot of us are beginning to explore that quite a bit these days. So this is one of the differences. There's a lot of differences, but this is one of the differences between streams and also what is the reactive streams that we are getting really excited about moving forward in reactive programming. And one of the differences is streams is sequential versus parallel. And again, I'm digressing from the topic, but I think it's pretty relevant to still keep that in mind. Whereas in the case of reactive streams, it is synchronous versus really asynchronous that we are really looking at in terms of the execution mode. That reactive streams offer synchrony versus asynchrony. But on the same note, when you do sequential, entire pipeline is sequential, or parallel. In other words, no segments. So there is no segments between your pipelining when it comes to your streams in Java 8. Either the entire pipeline is sequential or the entire pipeline is parallel. On the other hand, what is the reactive stream? The reactive stream, what does it do? The answer for that is it depends. It depends is the golden word of consultants, isn't it? We never give a straight answer. We always say it depends. Depends is a very dangerous word. Don't use it all the time. But in this case, it truly depends. Well, okay. Well, how does it really depend? Well, if you use, and again, I'm not suggesting this is a great API. Took me a while to really figure this out. But if in the reactive stream API, if you called subscribe on, then this is going to be no segments. So in other words, if you use the word subscribe on in the case of reactive stream, you are going to provide a thread for it to run. There are no segments. This is very much like your parallel versus sequential. The last one actually wins, and the whole thing runs in that particular thread. But it turns out there is also an observe on, and the observe on gives you the segments. So if you were to call observe on instead of subscribe on, then you can say, I want this part to run sequentially, this part to run in a different thread, this part to run in a completely different thread, and you can have segments in your reactive stream library, whereas Java 8 doesn't quite give you that capability. So those are some of the differences. The point I'm trying to make here is we need to be really aware of the semantical differences and capabilities of the libraries we are dealing with. Otherwise, we get misguided, and then we are surprised at the behavior of the code. And that is one of the things I normally look at when I look at APIs these days, is to say, hey, semantically, what do you treat? Do you treat your pipeline as segments, or do you treat them entirely as the same flavor? Java 8 treats its entire segment in one flavor, whereas reactive streams gives you the capability to alter it depending on which function you are using, and you can go back and forth with it depending on what your needs are. So that is something to keep in mind, is that as you can see here, this dictated the entire stream's behavior. It is not that the transform worked in parallel and the for each worked in sequence. It is entirely the entire sequence that worked in that particular mode. That's basically what you are getting out of this. Well, let's talk about observing the thread really quickly to see how this actually works. So to understand how this segment works, let's get rid of a few things and work through it. So let's go back to this transform method. In the transform method, let's output right here a little t colon. Let's put the number that we are working with. And then let's go ahead and output, let's say, the thread information. We'll say thread.current thread, so we can take a peek at the thread of execution of the transform method. Now, in this case, of course, we have the transform method that's displaying this particular data. Now, in the main, of course, let's go ahead and use this particular using the stream itself. We'll say stream and then dot map, and we will simply take the element and call transform, and then we will pass that to the element. Then we'll say for each, and within this we'll take an element, we'll simply throw it away, not do anything. So this is a sequential execution as you see it, but I'm going to print the thread of execution that is going to run this particular piece of code. So when I run this little code right here, I wanted to take a look at the thread of execution. A, it's sequential, no surprise, but B, it's also the main thread that's running it. So you can see main 5 main, so the whole thing is running in the main thread, so there are no surprises in there. On the other hand, if I were to run it as a parallel stream, then you will notice that it actually runs in parallel. But what thread is going to execute the parallel execution? Well, in the case of Java, there are a few things they did a little differently. I'm of the opinion that life's lesson is this: we solve one set of problems only to create a new set of problems. This has been my life's lesson. We solve a problem, and the minute somebody solves a problem, I ask them, what did you create now? And the answer usually is, I don't know yet. And that's a very reasonable answer in my opinion, because we tend to do this quite often. We solve a set of problems only to create a new set of problems. Look back in time for a minute. What did Java 1 really do for us? We created threads, and this was a beautiful wonderful time because you can do thread, you can do concurrency. Isn't that wonderful? One set of API to program. You don't have to write different code for different operating systems. This was awesome. You know, after some time in life, you usually, I don't want to be a pessimist in life, but usually end up asking the words, what's the catch? Well, the catch is, well, we realize that threads are really not that lightweight. It is not really a really good idea to create thread after thread after thread. We realize that that's not what we want to do. What did Java 5 do for us? Java 5 introduced executor services. What a great idea. Absolutely, that was a good API. We really enjoyed it. We had a pool of threads, and eventually we realized it's a pool of problems. Well, what is one of the problems? It really hurts when you run into problems like this. I remember one day, as everybody says, I had a code that actually worked. And it was working just fine. And I'm a workaholic. I usually code when I eat, and I eat when I code. So I took my little program to dinner with me. As I was having meal, I was running the program. And this program actually took only about a few seconds to a minute to run most of the time. And then as I was having my meal, I suddenly looked at the program, and it felt like it's been running a little longer than I thought it would run. So I kind of waited for maybe a few minutes, and it never actually terminated. So I was a little surprised. I said to myself, why would this program not terminate? And that's when I discovered a problem which is called pool-induced deadlock. So what is pool-induced deadlock? Let's think of a little example of what a pool-induced deadlock is. Imagine for a minute that we have one pool, and I apologize for elevating the gentleman in the front row as threads in a pool, but let's assume we have two threads in the pool, and this pool only contains two threads, and the threads are going to solve the problem we're going to provide for them. Assume that the problem I'm going to give is a small problem, which is this size, and I throw this problem onto the pool, and he says, hey, that's really small enough for me to handle. He handles it, and work is done. But what if I provide a problem twice the size as reasonably can be handled? He says, gosh, that's a bigger problem. What does he do? He breaks the problem into two and throws it on the pool and sits back like a boss and says, my job is done. I took the problem, I divided it, threw it in the pool. I will wait for the response to come back. When the response comes back, I'll combine the result and return back. And he just sits there and twiddles his thumbs waiting for the result to come back. The next gentleman, who is the thread on the pool, says, hey, I can handle it. Looks, there are two jobs on the pool, picks one small enough to execute, finishes it, takes the next one, finishes it, and he's done with both of his job, who did most of the work. And then, of course, when the result was completed, you collect the result and send it back. Well, looks like things work really well. Now let's say we give a problem which is 4 sizes of the problem that we can handle. What does he do? He breaks the problem into 2 and throws it on the pool, a divide and conquer. There are 2 problems now of bigger size. The second thread in the pool says, my job is to split this into half, breaks and throws into the pool and says, I'm going to wait like a boss for somebody else to handle. But unfortunately, who is that somebody? We are the threads in the pool, and now we have pool-induced deadlock. Because the 2 threads in the pool divided the work and waiting for some other thread to do the work, but unfortunately there are no some other threads in the pool. This can be really annoying because the problem is not induced by you. Your code doesn't have deadlock. It is that the way the pool was implemented causes the deadlock. In other words, there are threads that divide the problem and take a break waiting for some other thread to do the work, kind of like the corporate world, isn't it? So somebody says, my job here is done. I just sent it to them and waiting for them to finish, right? Well, obviously that's not going to be really a fun way to do it. And this is why we had what is called work stealing. And this introduced what's called the fork join pool. And the fork join pool says, this was introduced in Java 7, which is the fork join pool. And now we are saying, when you divide a problem, you be part of the solution and not just dividing the problem itself. So we are removing the pool-induced deadlock issue in the code by saying, I have a problem which is bigger than I can handle. I broke the problem into 2, throw one part into the pool, but the other part I'm going to be involved in solving it myself. And so the thread that divides the problem also participates in solving the problem as well, so it doesn't really end up wasting the thread waiting for something else to really execute that particular call. And that, of course, becomes the way to solve that particular issue. So for this, we use what's called the fork join pool for doing the work. So where I'm getting to with this is that Java 8 uses the Java 7's fork join pool for parallel streams. But of course, there is also what is called a common fork join pool. And what is a common fork join pool? Is a pool that is maintained by your application, and you can simply use that pool, and that's what the parallel stream uses. It is something important for us to keep in mind because we're using that common fork join pool anytime we use the parallel stream, unless we have other configurations to override it, which we'll talk about just a little bit later. So it's going to use the common fork join pool. So to see this, let's go ahead and run the code and see what we see as the output. And notice right there is the common pool. The fork join pool.common is being executing the output. But I also want you to note very carefully something else. Notice the number 8 and 2 and 1 and 9. Those were all handled by the common pool worker 4, 11, 15, and so on. However, did you notice that 7 was executed by the main itself? Just keep that in your mind. We'll come back and talk about this later on, how main suddenly ended up being here. But notice that the fork join pool is actually executing this code with one of them being executed by the main. There's no guarantee as to which one it would be. It so happened that 7 is being executed by it. Okay, so it really likes 7, but that's purely arbitrary, right? So in this case, of course, it's going to, okay, I give up at this point, right? So the main is messing with me. It says, let's mess with Venkat today. But the point is that it's going to execute one of them, whatever that could be. All right, so we kind of know the observing the thread, but what about the order of execution of the code as it runs through it? This is something also we need to be careful about. So going back to this code real quick, let's go ahead and remove this printout for a second. Let's go ahead and perform the transform like we did. But in here, let's go ahead and say system.out, and we will go ahead and say a print line to print it. Now, in this example, let's run this sequentially, first of all. And as you would expect, when I run the code, you can see that the output are exactly in the same sequence as the original collection was. A list is an ordered collection. Because list is an ordered collection, the iteration happens in the same order, and you can see the values 1, 2, and all the way up to 10 being printed. But because a list is an ordered collection, the question is, what's going to happen if I do a parallel stream? Well, when you do a parallel stream, there is no guarantee to ordering at that point. So as a result, the map will run as fast as it can. And when the map completes for that particular value, the for each is ready to run. So here's a good news and a bad news. Imagine you are doing a print job on this. You call your client and say, I've got a good news and bad news. The results were really fast, but the pages are jumbled up. Good luck, by the way. So that's not going to be really fun when the order of the output is completely jumbled up. As you can see right here, there's no guarantee on the order of execution. It was 1, 9, 6, and 2. But when I run this one more time, notice it is 5, 3, 10. Who knows what this ordering is? It could be just about anything every time you run it. There is no way to tell. Well, that's basically the consequence of running it in parallel. Well, there are a couple of things we need to be aware of. So we need to know that some methods are inherently ordered. So by nature of what they are inherently ordered. You never have to say order it because by definition they're going to be ordered. Some methods are unordered, so unordered, but may have an ordered counterpart. So you may have an equivalent of it that you can use for that particular operation. So it depends on the API. You have to take the time to study it to know whether it imposes ordering naturally or maybe it doesn't, and maybe there's a counterpart for imposing ordering. It becomes a lot more easier when you think about the logical meaning of the methods, if you will. We'll look at some of these later on. But for now, if you look at this code right here, the for each is unordered, and that is the nature of it. When you run it, there is no guarantee here on ordering. On the other hand, there is a counterpart to it called for each ordered, and for each ordered tells you that I want to impose ordering in the terminal operation. And that can be really effective. When I run this code, notice it is imposing the ordering on the data, and no matter how many times you run, it's going to be exactly in that particular order, and that is the for each ordered. Now, make no mistake, for each order does not convert your execution pipeline into sequential. This is concurrent execution, except that it says, I will not run until the one before me has completed. So it imposes ordering, but not sequential execution. There is no thread guarantee at this point. So to illustrate this point, let's go back to this code and put the printout on the transform method. But we will also go ahead and call a method here where we call it as print it and pass the E to it. Now in the print it method, we will simply print it. So let's go ahead and bring in the print it method. So this becomes the void print it. And in this case, of course, we'll take the number and we'll put a P right here, and we will print it right now. And that's all we're going to do. So we put a P and the number we want to print, and then the thread information we're going to provide right here. Now when we run the code in with the for each, let's go back and run this in for each for a second. Notice that with the for each, there is no guarantee at all. As you saw from the output, there is the T which is transforming the output right here. All the transformation are happening. But notice when the 10 got finished, that got printed. When 5 got finished, the 5 got printed. So they're all just printing in different order. The P10 appeared before P5, showing that there is no guarantee of ordering of the printing. They just went haywire depending on whatever order that things were finishing. If I said for each ordered, on the other hand, if I execute this time, even though the transformation all happened in parallel, notice that 9 happened before 2 happened before 5 and 4. But on the other hand, when it comes to the printing, notice it follows the ordering 1, 2, 3, 4, and so on, and that follows the ordering. This is worker 15, as you can see. This is worker 4, as you can see. So there is no guarantee which thread may actually execute it, except it says, 4 says, I will not execute before 3 has finished. Similarly, 7 says, I will not execute until 6 has finished, but that doesn't mean they are actually sequential. They're running in parallel, except that it says, I will not complete my job until the one ahead of me completes it. Keep in mind that for each ordered does not guarantee ordering unless the stream guarantees ordering. That is something we need to keep in mind. If a stream is on a list guarantees ordering, the for each ordered guarantees ordering. If your stream is on a set doesn't guarantee ordering. For each ordered cannot suddenly make up some ordering that didn't exist. So for each ordered guarantees the imposed order doesn't make up its own order along the way. So if the stream is unordered, there is no guarantee of ordering. But if the stream was ordered, then there is a guarantee of ordering is going to follow. That is something we need to keep in mind in terms of how this ordering works. So this can be really useful when you do want to execute things in parallel, but you do want the terminal operation to have certain ordering imposed on it. That doesn't mean you can take any terminal operation and throw an ordering on it. That's not the intention. There are some with no ordering. There are some with ordering counterparts. It depends on what API you're dealing with, and you have to really work through it depending on what you're working with. So we saw how to control the ordering of execution. Now let's talk about parallel and what are some of the consequences of using parallel as well. So when it comes to using parallel, what are the things that can run in parallel? Let's go ahead and again discard the output over here. Let's only focus on the filter. Given a value, I call a check method and pass the value to the check. Well, the filter is going to run in sequential mode right now. Let's take a look at what the check is going to do at this point. So here is the check method. So what does the check method do? It returns a Boolean. And at this point, given a number, I'll say C and print the thread information. And I will simply return a true to accept all the values given to me. So the check is simply printing the thread information, returning a true. And the filter, of course, is simply calling the check to perform the job. When I run this code, you will notice that they are appearing sequentially, all in the main thread. That's no surprise, of course. However, if I were to go back here and say parallel and stream, well, that's going to run the filter in parallel as you would expect. So when I run this, you can see all the check running in parallel, and that's what we just saw here. So the filter is happening in parallel. Similarly, we also already saw that map is running in parallel also, so that's no surprise. But the question is, what about reduce? Let's understand what reduce is first, then we will talk about whether it can be run in parallel or not. So what does reduce really do? So to understand this, let's take this collection of numbers we have on our hand, and we will say dot reduce, and in the reduce I say 0, comma, and we will say total, comma, element. In this example, we'll simply return, call a add and say total, comma, element. So all we are going to do here is simply add the values when we are totaling it. That's what we are going to really do. So all we are doing in this case is just doing the totaling of the operations, and this add is simply saying, given the value total and E, return a total of those two. Let me come back and explain what this really means in just a second. So we'll take an add, we will say this is A and B, and what I'll do here is to say result is equal to A plus B. I will return the result, but before I do, I will go ahead and print out right here. Let's go ahead and say output, and we will output, let's say A is equal to the given value A plus, let's go ahead and say B is equal to the given value B plus, let's say result is equal to the result over here, and then plus, and then we will go ahead and say right here, plus thread dot current thread. So I'm going to display the A value, the B value, and the result, and return it. Let's understand what really this means as an add value. Let's assume for a minute that I want to total the age of everyone in this room, and we'll start with him. He's not smiling at me at this point. I'm not going to ask for your real age. So what I'm going to do is I'm going to give him a value of 0. And what does he do? He takes the value 0, adds to his own age, and passes it down to the person next to him. So what does he do? He gets the age of total of all the age for everyone to his right, totals his own age to the value, passes it down. And what does he do? He takes the value of age given to him, totals his own age, and you see where this is going. So this is going to move through the room. We can sit there and watch this trickle through. And let's, like passing a post-it note. Everybody gets a post-it note. They strike the number on it, add their own age to it, write the value on it, passes down the post-it note. And what am I going to get at the very end of the room? Either the age of everyone in this room or an overflow, right? No, just kidding. But the point really is that we are going to get a value at the very end of the room. We're going to get the total of everybody's age. Well, that's kind of what the reduce method is doing. Reduce is a pretty iterative, but it really has a feedback loop. So the way this feedback loop works is you have some kind of an operation. We'll call it as op. And what the op does is, suppose you had elements, let's say E1, E2, E3, and so on. And what it does is it takes an initial value, and I'll come back and change that initial value a little later on. For now, allow me to use the word initial value. Soon I will tell you why that's a really bad idea. Use that name. So we take the initial value, we perform the operation with this value E1. That produces a result for us. We take that result and perform the operation once more, but this time with the second value in the collection. That produces a result again, and we apply the operation this time, but with the third value in the collection, and then that produces a result, and then we keep going until we get the final result out of this operation. That becomes the result of the entire operation that we are working with. So this is exactly how the reduce operation actually works, that it starts with this value, perform the operation with the first element, takes the result of it, feeds back. So you put an output, which then comes back as an input to you for the second element. You take that and you bring it back as an input for the third element, and you keep moving forward. And this is why in some languages they call reduce as aggregate. In other languages they call it as fold left. So this is to give you an impression of you're folding this left like you fold a mattress, or a mat rather. So you essentially are folding it through, and that gives you an ability to just walk through this in one direction, and that is essentially what it's doing. Well, if I look at it from that point of view, because the output of one operation is needed as an input for the next, and the output of that is needed as an input for the next one, it appears though that this is going to be done sequentially. But it turns out that's really not the case. Let's get back to this room again for a minute. Well, this room has quite a number of people here. We got several rows in here. If I'm going to do the reduce sequentially, that's a good time for me to go get a cup of coffee and come back. Because as you are going to pass the post-it note around the room, as it moves through every single row, that's going to take several minutes for us to get this done, because we're going to go do this sequentially. But we could do this quite differently though. Here's an idea. I could simply say, folks, do me a favor. Every row, do the totaling concurrently, which means on the first row, you will start with the 0, and it starts trickling through from my left to the right. Second row, the gentleman over there starts with the 0. Same way, the third row, the gentleman over there starts with the 0, and so on. And as it trickles through, the lady over here is going to have the data for the first row. The lady on the second row gets the data for the second row. The lady on the third row gets the data for the third row. And then we can go that way. Then what happens? At the end of the sequence, the data is all gathered to the edge of each of the rows. Then I can work with the people on the edge of the rows and say, let's trickle through from the end of the room all the way to the beginning, and she will eventually have the total of everybody's age in the room. And so in this case, how many steps did we take? We take the number of rows in this room, all that are done in parallel, that's one shot, and then we do this way, that's 2 shots, and we can get the result right after that. So that gives us an idea about how we could possibly do this more concurrently. Well, so that gives us hope that reduce can be done in parallel. The question is, nice theory, Venkat, but does it work that way is the question, isn't it? So let's see if that's actually true. So I'm running this sequentially, as you can see right here. So let's go ahead and run this code and see what it tells us. Oops, a compilation error. Okay, we'll fix it. So in this case, of course, I'm going to, A is A, B is B, and the result is result. And then, of course, does anybody see the error? All right, so I'm sorry. Line 24, I assume? All right, what did I do on 24? Take away the plus over here. All right, sorry, I'll walk through this. Here's a plus, and I need this plus, right? And then I need the plus. After the result, all right. So result and then plus here. Is that what you wanted? What a picky audience. Are you happy now? Okay, thank you. All right, let's go ahead and try this. My faith in pair programming just got restored. Thanks for that. So when I run this code, did you notice how the value is being fed back into it? So we take a 0 and a 1. The result is a 1. That feeds back as 1 here. 1 plus 2 is 3. That feedback as 3. 3 plus 3 is 6. That feedback as 6 plus 4 is 10. Feedback as 10 plus 5 is 15. So every time it's the feedback plus the current element gives the next result all the way to the end. So that seems to have worked really well. Okay, so far so good. Oh, what about the threads? The threads are all main thread, of course. Okay, that worked really well. Let's give it a try again. But this time around, let's go ahead and say this is going to become a parallel stream. And when I say this is a parallel stream, when I execute this, notice that they all ran in parallel. Well, they all ran in parallel, as you can see. That's all the fork join pool thread, as you see in here. But when you look at the result, I'm going to shorten this just a little bit so it's easier for us to see. So I'll just simply say R is equal to, rather than the result is equal to. Let's see if that comes into a line. Okay, that's a little bit better. So if you notice over here, this is running in parallel, but did you notice multiple of these having the value 0 to begin with? Because that's what I mentioned earlier, is many rows can start concurrently. That's kind of the idea, is that we are starting with all these values. He pointed out that 7 is still in main, right? Okay, I surrendered to main today. Main wins the end of the day. Look at that here as well. So I don't know what it is with main, but as far as main is happy, I'm happy. Okay, so you can see in this case that you have the thread executing concurrently in the fork join pool, as you can see in this example. That brings up the question, okay, that's all great, right? Shouldn't we just be happy about it, that it's running concurrently? Almost. Let's go back to this one more time and run it sequentially as a stream. Notice the result is a 55. Great. Now, on the other hand, I am going to say, hey, I want to add my own age to everybody's age in this collection, isn't it? So let's go ahead and put my own age. You don't believe it, right? So that's basically what I'm going to put right there. And then I'm going to say, run this concurrently to execute this right away. Well, sequentially rather. So 55 plus 30 is going to be 85 the last time I checked. Run the code. Yes, that's 85. That worked really well. But I'm going to now change it to a parallel stream, and this is called trouble. And the reason this is trouble is this is not an initial value. This is what I said earlier. Allow me to use the word initial, but very soon I will tell you that's a really bad idea. This is not an initial value. So when I run this code now, notice the result is not 85, it's 355. What really went wrong? So we need to understand a couple of different ideas very clearly. So what is this value that you pass right here? So in other words, we need to understand a few things. Reduce does not take an initial value. It takes what is called an identity value. So it's very important for us to understand what we are working with. So this is called an identity value. I don't have a clue what that means. It depends on your model, your domain, your application. I know that for integers and for plus, the identity is 0. So what is identity value? It's a value. It's a value when performed with an operation will give this whatever value that you operated on. For example, x plus 0 is always x, so that makes 0 as an identity value for sum. Similarly, for integer, star or multiplication, identity is 1. Because we know that x times 1 is always x. So in other words, we need to understand what an identity value is. Not intending to throw terms at you, but then the next question is, what we work with should be a monoid. So what does it really mean? Well, a monoid really has a few requirements. And the requirements are that A, that when you give it, there is an identity value. And B, that the operations you perform will result in a value which belongs to the original set as well. So there are certain rules like this for an operation to be monoidic. And if the operation you're performing is not monoidic, if the collection you're working with is not monoidic, you cannot use reduce with it. This is why it goes a little deeper than just dealing with the API. We really have to understand what we are working with. Otherwise, we will start throwing things around, and the code doesn't behave the way we expect, and then we kind of get worried and start debugging. But stepping back and understanding the rules of engagement becomes a lot easier for us to work with. So this is one of the reasons why we have to be very careful. This is not an initial value, it's an identity value. So when you work on your own domain, your own application, when you're trying to use reduce, pause and ask the question, what is an identity value? And don't pass to reduce what is not an identity. Why? Because it may not really be a problem today when you're writing the code, because you're writing it sequentially. But 4 months from now, one poor developer, also known as victim, modifies the code to run parallel, and everything goes haywire. and they are not sure why things don't work, and they may not really realize at that point that the input given was not an identity value, and things are really becoming poor in correctness. So we need to take the time to understand what we are passing to it. That becomes very highly critical. So that tells us about reduce. Good news, reduce runs in parallel. Bad news, we still have to understand what we are doing to make sure we're getting the right results with it. That's very critical. So when it comes to using streams in parallel, one of the questions to ask is, how many threads are we going to get? How many threads are we going to use? We have to understand the difference between IO-intensive problems and computation-intensive problems. So the question I want to ask is, how many threads? To understand this, I'm going to pose two questions here. The question here is, how many threads can I create? This is a bad question. This equivalent of this question is, how much food can I eat? This is not a good question to ask. We know this. Because I can eat as much food I can hold, but that's not really healthy. The real question to ask is, how much food should I eat? That's the real better question. In a similar way, the question I should ask is, how many threads should I create? So oftentimes the difference between can and should makes a big difference. So we should really ask the question, how many threads should I create, not how many threads can I create? I was working on a project one day, and we were running at a maximum performance at that point. We were having as many threads as the number of cores. And one of my colleagues said, I want more. I said, no, you don't want more. He said, no, I do want more. The sequential code took 20 minutes to run. The parallel code took 5 minutes to run. We increased the number of threads. Now it took 1.5 hours to run. So you have to be very careful because there's a tipping point after which you're not going to get better performance. So the question really is, how many threads should I create? I'm going to use a very silly example for this. There are two kinds of computations we perform. One is computation intensive, and the other is IO intensive. When your operation is computation intensive, you are constantly churning through doing your work. So to understand this, I'll give you a silly example of 4 monks. You know how monks are the politest of people on earth. They always look out for other people's feelings, other people's comfort. And so the 4 monks go to a gym, and they realize there are only two treadmills. So 2 monks get on the treadmill, they turn it on, and they look around and they realize there are 2 monks waiting for the treadmill. They say, how rude of me to be running on the treadmill when you are waiting. So the 2 monks get out of the treadmill, only for the other 2 monks to get on and turn it on. And they'll say, oh, you're waiting for the treadmill. How rude of me to run on the treadmill. And they get down. So none of them actually work out that day because they're very polite to each other. That's why it's good to be rude sometimes in life, isn't it? But no, the point really is that this is exactly what's going to happen when you have computation-intensive thread. A thread, the task that you have is going to get on the CPU, while the other task waiting says, hey, I want my turn, you get off the CPU. And so they end up trashing each other a lot. So the moral of the story is, for computation intensive, number of threads should be less than or equal to number of cores. So you should never, ever, ever give more threads than the number of cores. If you give more threads than number of cores, you will actually get poorer performance in your application. On the other hand, for IO intensive, number of threads may be greater than number of cores. But how many, we don't know yet. We'll come back to that in just a few minutes. So the point really here is that when you have a computation-intensive job, you can only give as many threads as the number of cores. If you try to give more threads than that, you will lose performance. In a similar way, for an IO-intensive, you have a bit more leeway. Why? Because you have the number of threads, but the tasks are really going to sleep while the tasks are sleeping, you might as well use the CPU for another job that becomes really useful. Well, that begs the question then, how many are we really talking about? Well, to answer that question, let's draw a little formula, and the formula is number of threads is less than or equal to, keep in mind, it is less than or equal to, not equal to, less than or equal to, and in this case, we're going to say the numerator is number of cores, and the denominator is 1 minus the blocking factor. So where the blocking factor, the blocking factor is 0, less than blocking equal to the blocking factor less than 1. So this becomes the formula for the difference determining the number of threads. So the number of threads is less than or equal to number of cores divided by 1 minus the blocking factor, where the blocking factor is a value 0 less than or equal to blocking factor but less than 1. If the blocking factor is equal to 1, you have a deadlock. So definitely you don't want that, but less than 1. Let's see if this math holds. If the blocking factor is 0, the denominator becomes a 1, which means number of threads is less than or equal to number of cores divided by 1, which is number of cores, which is what we said up here. On the other hand, if you're dealing with the I/O intensive, I'm sleeping half the time, then what happens? Well, when I'm sleeping half the time, another task can use the CPU, which means 2 threads could use a single CPU, which means you can have twice the number of threads as the number of CPUs. Is that, of course, is that really true? Well, if the blocking factor is 0.5, then 1 minus 0.5 is 0.5. Number of cores divided by 0.5 is 2 times the number of cores, so the number of threads is less than or equal to 2 times the number of cores. If I'm sleeping most of the time, 90% of the time, 0.9, 1 minus 0.9 is 0.1, number of core divided by 0.1, 10 times the number of cores, which is a very grim realization. If I have 256 cores on my machine, if my job is computation intensive, I can have 256 threads, not thousands. If I'm doing I/O intensive, and if I'm sleeping most of the time, I could go up to 2,500 threads, not anymore. So it's very naive to think the number of threads is equal to the amount of memory we have. No, not at all. It is actually limited not by memory, it's limited by the CPU number of cores we have. So we have to be very careful how many threads we actually create. This brings the point to what we saw so far. This is why I said they're very smart in what they do. So we talked about the formula. Let's talk about the default number of threads for that reason. So to understand this, let's go back to the code right here. Let's get rid of all of these for a second. Let's now ask the question, what do we have as number of threads? So let's go ahead and bring in java.util.concurrent.star. And then in the main, we will say over here, we will say output fork join pool, and then, of course, dot. And we will go ahead and say common pool. So we'll ask for the common pool and query the common pool that we are getting. Now when we go back and run this little code, let's see what it tells us. It is giving us the details about the common pool in the system. Remember, common pool is what the parallel stream is using by default. And if you look at the common pool, did you notice parallelism is 7? What in the world does that mean? Let's come back to that in just a minute. Let's output right here, runtime.getRuntime.available processors. I'm asking for how many cores I have on my machine. And knowing how many cores I have on my machine, we can relate to this idea. So the first number is number of cores. The second is the details about the common pool. I'm going to take a look. So when I run this code now, it tells me I have 8 cores on this machine, which is a lie, by the way, but we'll go with it. So it says I have 8 cores on this machine, but it says parallelism is 7. Do you feel cheated by 1? No, it's not, because this actually has an external member, and you know which one that is. It's the main that is so busy with 7. So the point really is that main is also part of this pool. It's the external member. They've been very careful about it, if you noticed. If they had created 8 threads rather, then they have one more the number of cores when you include main, and that would violate the formula we talked about a few minutes ago, because the formula did not say approximately. It said your upper limit is number of cores, don't go even one over it. And that's why they were very careful selecting one less for the common pool, because the main is actually participating in it as well. So when your code executes, the main has the work to do, and it joins with the common pool, which is also the member of it. So that is the reason why you see a 7 in there. So the default number of threads is equal to the number of cores on your machine. Let's revisit the problem we've been working with really here, just to see the example. So if you notice the transform method, if we go back to the main, and in the main, I'm going to say right here is numbers.stream, and then let's go ahead and say map, and we will call the transform method right here, and pass the element to it, and then in the for each, we'll simply throw away the result we get out of this. Now when we go back and run this, in parallel stream, so here is a parallel stream, and execute this parallel stream right here, you will notice that it's running, but more important, notice something else real quick. I have these values 1 through 10 right here, but I'm going to change it to another set of values, let's say 11, 12, 13, and so on. Well, I've got 20 values on my hand right now. So given the 20 values, remember I have 8 cores on my machine, so how is it going to be split? You would say it's going to be 3 batches. The first 8, the second 8, that's a 16, and then a 4 coming through afterwards. Let's see if that's really true. Go ahead and run it, first batch, and here's a second batch, and here's the third batch. So you can see that it ran in 3 batches because it is based on the number of cores that I have. Hey, for the first time you can see main doesn't have 7. Bet to it eventually. So the point really is, in this case, it's the first batch you are seeing here, and then when that's completed, the second batch, and then of course the third batch is running. So that's split across for these 3 different things. That's how it's going to schedule it based on the common pool of threads. Then the question is, how do I configure this to modify it? Good news and bad news. Let me give you the good news, and I'll give you the bad news after that. The good news is you can configure this at the JVM level by using this flag. It's called the java.util.concurrent.fork.join pool.common.parallelism. I love this flag. Finally, something larger than my name. So the point really is, that's a configuration property you can specify to change the parallelism, meaning you want to have more threads in your parallel stream. Now, I'll tell you why this is a terrible idea, though. So when I go back and run this code, I'm going to run config, and I'm going to ask it for 100 thread. Run config is just a script I wrote where it runs the JVM, but it runs it with that flag, so I don't have to type that in here manually, making my life a little easier. I'm running with 100 threads. You can see it all finished in one burst right there because I gave it 100 threads, not just 8 threads. So you can see that all ran in parallel with that many number of threads, as you can see. But having said that, though, this may not be really such a smart thing to do. Why not? Well, the reason is, let's go ahead and take a slightly different example just to see why this may not be such a good idea. Well, here's a little example I created where I am writing a compute method, and all that it is doing is 2 loops to perform the sum of square root of numbers, just to make it computation intensive. And I got a max of 1500, and what I'm doing here is to create a 0 to max, and I'm running it as a map to double, and I'm performing the sum operation on it. And this is running sequentially, as you would expect in this case. That's what this is doing. Let's go ahead and try this out. So I'm going to go ahead and say time it and run.sh, and I'm going to run this sequentially, and this is going to take some time, produce some result of this computation. It is just burning the CPU at this point to run this sequentially. One thread is doing the work, one CPU core is involved in it, the other 7 are sitting and watching it, right? So that's basically what's happening right now. It took about 17 seconds to execute, as you can see, and the result is 2.24 times e power 12. Just keep that in mind, 2.24 e12 in about 17 seconds. I want to make this run faster. So I say dot parallel right here, because this is giving us a stream. I can't do a parallel range, but I can make it parallel by calling the parallel method. So this is going to run in parallel. So I go back and run the code again. But this time, notice it only took about how much time? 4 seconds, give or take, and the result is still exactly the same as before. So that tells us the code ran correctly, but it definitely ran faster. Now the question is, how can I get a faster result for this problem? And the short answer is, don't even try. Because on this machine, this is the best you can do because that's how many cores you have. Because it's computation intensive. This is why we have technology like Spark, because Spark says, well, sorry, you've run out of your capability. That's how many cores you can have on the machine. You cannot get more cores on your machine, obviously. You cannot put more threads than this. You got to distribute it horizontally on a cluster, and let's make it easier. And that's why we have technology like Spark to make it happen. But what if I get greedy and say, I really want to increase it? So in this case, I'm going to say run config. I'm going to give it 1,000 threads at this point. And remember how much time it took to run, 4.48 seconds almost. Now I run it with 1,000 threads on this machine. How much performance am I going to get out of it? Notice actually it took 5 seconds now and not 4 seconds. By increasing the number of threads, we actually ended up running slowly. Like I mentioned earlier, I worked on problems where the concurrent solution with as many cores as the number of, as many threads as the number of cores would give me a certain speed. When I increase the number of threads, I actually started slowing them very drastically. So when you look at the number of cores and the performance, you will get the peak performance when the number of cores equal to the number of threads, rather number of threads equal to number of cores, and then you keep increasing the number of threads, you actually get less performance out of your code because there's going to be more trashing in your application. You're not going to get benefit out of that. That's a limit we need to really know with this. The other problem with using this approach is this is modifying the configuration for your entire pool of system, which means what we are running on it is going to compete with the common pool. If you have a lot of computation-intensive jobs and I/O-intensive jobs mixed together, that's going to be really terrible because they are going to be competing for the same pool. You're not going to get really good performance out of it. These are easy solutions to reach to get into trouble very quickly. So that is one of the biggest problems with it. One other thing you could do is to configure this programmatically. Well, to configure it programmatically, you have to still be careful. What does it mean to configure it programmatically? To understand what that really means, let's go back to the previous example we saw earlier. In this case, what I want to do is know how this is going to run and when it's going to run. To understand this, let's go ahead and create this numbers.stream, but we will send it to a method called process. So the process method is going to process the stream. So here is my public static void process, which takes a stream of integer. And in this case, I'm going to say stream. In fact, to make it blatantly clear, notice what I'll do here. I will take the stream and I will say dot map, given an element called transform, and then pass it to the element, and then I will pass that stream over to process. Well, within the process, what I'll do here is simply say stream dot for each, and I will take the element and just discard the value. When I run this code, the stream was mostly built in the main, but the terminal operation is being called within the process method. When I run this code this time around, you will notice that the whole thing is running in the sequential thread. No surprise over there. However, notice what I'll do here. I'll say fork join pool, and I'll say pool is equal to new fork join pool of, let's say, 100. And then I will say pool dot over here submit. And I'm going to submit to the pool. And in this case, I'm going to provide a little lambda. And within the lambda, I'm going to execute that. The point I'm really making here is that your terminal operation is running within another pool. So in other words, in short, the question is, which pool executes your code? It's not the pool thread or the pool in which your stream is created It is the pool from which your terminal operation is executed. So it doesn't matter where the stream was born. It matters where its terminal operation is executed. Because the terminal operation now is executing within the fork join pool we created, this entire thing is going to run in parallel within that pool. What was done before was the terminal operation was executing within the main, but this time within the custom fork join pool that we are creating. As a result, let's see if that's actually true. Let's run this code and see. And well, actually, we want to wait for a termination. We'll do that right here. So pool dot shutdown, and then we will say pool dot await termination, and we'll give it about a 10 seconds time unit dot seconds, a lot of time than it needs. That's going to require exception handling. We'll just simply throw it away, throws exception, just to communicate that back over there. And so given this, what is it going to do? It's going to wait for the pool to terminate before it completes. And so we can actually see that, well, in this case, it's still running it sequentially, isn't it? Let's see why that's actually the case. This is the thread fork join pool. The transform is happening right there. So that should be running that within the submit, within the fork join pool. We should be running it. I'm not sure why that's, I probably messed up something here. So this is actually the for each executing the terminal operation within this pool. Let's make sure I'm doing this right. So I created the pool right here. I'm calling the submit on the pool, and this is going to be called within the pool right here, and then the shutdown has to happen right there. Let's make sure the process is being called, the map transformation, and then I'm calling that in here. So I'm a little surprised why that's doing what it's showing, but that should be running within that pool. Let me try this just one more time, just to be sure it got compiled and it's running it. So I'm wrong here. It is saying worker pool. Sorry, say that again. Did I do that sequentially? Yes, thanks for the catch. You are right. I'm sleeping at the wheel. All right, at least one of us is awake in the room. That's awesome. So that's parallel stream. You are right. Thank you. Now you know why it did. That's the right behavior. I'm glad it did the right thing. Now run it parallel. Thank you. I just assumed that I had made it parallel. Thanks for saving that. There you go. So that's basically the whole point, is that it's running based on where the terminal operation is running, not where the stream was actually created. So that makes the point as to how it executes. That brings up one more question. Does it really mean it is faster? Well, we saw this earlier. It doesn't mean it's always faster. It depends on various different factors. I'll give you a really trivial example about this. Imagine you have 2 children at home. You're running out of sugar. You tell the kids, hey, why don't you go to the neighbor and get some sugar? One child jumps the fence. The other child goes to get the bike. You know which child is going to get you the sugar first? The one that jumps the fence, because that's the easiest way to get to the neighbor, isn't it? So in that case, you really don't want better performance. You want really a much more access through jumping the fence in this case. Just because you have parallel doesn't mean you'll get better performance. On the other hand, if you say go to the store about 5 kilometers away and get me something, the kid that jumps several fences goes to jail. You really want the kid that takes the bike and gets the stuff. So it really comes to 2 questions. How many objects you have on your hand to work with. If you have a lot of objects, parallel may make sense. If you don't have that many objects, maybe parallel is not a right choice. The other question to ask is, how much time does your task take? If your tasks are very fast executing, you're not going to get performance out of parallel, because you may really waste more resources creating threads than getting the work done. On the other hand, if your tasks are relatively quick, you can, not going to get performance. If they are taking time consuming, maybe you'll get performance out of it. I want to wrap this section with one other detail that is important to keep in mind as well. And one of the very important things about parallel is that when it comes to streams, we normally do what is called lazy evaluation. And there are consequences to this. So I want to illustrate that with the last example we're going to see here. Let's bring up a little example of a create person. And the create person has a bunch of people. Let's make Jill a little older here for a second. Now you have Sarah and Sarah, who are 20 and 22. Bob and Paula, 20 and 32. Paul is 32 like Paula is. Jack 2 and 72. Jill is 42. Let's say over here, find the first a lady who is older than, let's say 30. So how do I execute this code? The first lady, so I'm saying that you are talking about the order of execution in here. So how do I do this? So create people.stream, and then I'm going to say .filter. In this case, given a person, I'm going to say person.getAge is greater than 30. And then I'll say filter given a person, I'll say person.getGender is equal to gender.female. And then I will say find first. And once I find the first person, I just want to print it. So I'm going to output the result out of it. Well, I notice that I'm doing it sequentially. Execute the code. It says optional Paula. Well, it's optional because an object may or may not exist. I'll say or else will say no one found. So when I execute this code, it's going to say that in this case, the result I'm going to get is whatever the result I'm going to expect. Let's actually convert this. So .map, given a person, let's say get name. And in this case, of course, it's Paula. Well, that is sequential execution as we know. Now, notice the function we are calling is find first. What does the word find first actually mean? There is an implicit ordering in there, isn't it? The word first means ordered. So you don't have a find first ordered. It doesn't make any sense. This is what I was talking about in the beginning. There are some functions that are implicitly ordered. It doesn't really matter. So in this case, as you know, when I run the code, you can see it says Paula. It doesn't matter. Well, of course, I'm running sequentially, but it doesn't matter how many times run. It's going to be exactly the same result over and over and over. But the question is, what if I say parallel stream and run it in parallel? If I run this in parallel, though, notice that at this point, it doesn't matter how many times I run, it still will always be Paula. Now, we both know one thing. You don't run a code 1,000 times and prove it's correct, but you get the point. So the point really is that it is going to be exactly the same result no matter how many times you run it, because you said find first. Find first is always ordered. So in other words, it doesn't matter you ran it parallel or sequential, it's always the same result. But then on the other hand, let's take this back to sequential execution as a stream, but I say find any. I want any lady, not the first lady, any lady who is older than 30. Well, it turns out in this example, we got two people who are qualifying for that. We got Paula, we also have Jill. Well, the question is, who are we going to get as a result? Well, unfortunately, because it's sequential execution and because the collection is is ordered, you will have a bias towards Paula all the time, because find any is find first. Unfortunately, when the execution is sequential, there is no difference after all. So when I run this code, it doesn't matter how many times I run it, it is still Paula. On the other hand, though, if I were to turn this into a parallel stream, then, well, all bets are off, isn't it? Because it's running in parallel, it might be Paula, it might be Jill. I have no clue which one would it be. So let's give it a try and see what the system wants to think. So when I run this, you notice it is Jill, okay, at least once. Okay, so that's kind of where the parallelism actually kicks in. So it could be just about any, if you will. There is no guarantee as to which one it would be. That's one of the differences. But that brings up yet another important point. Let's go back to this example. Let's say find first one more time, and this is the first one. But let's go ahead and say this is going to be sequential, and we will say stream again. This time, of course, you know that it's going to be Paula one more time, but let's look at something a little different. Let's go over to the person class. In the person class, in the getAge, let's output age for, and then we will put the name of the person who we are asking the age for. We know one thing very well about streams. They are lazy evaluation, which means run sequentially in this example, it's going to ask for age of Sarah and Sarah, Bob and Paula. but it will never ask for Paul, Jack, and Jill in this example. And the reason is the minute it finds Paula, it's going to get out. Is that really true? Well, let's run the code and see if that's really true. And notice it asks for the age of Sarah, Bob, and Paula, but it never touched Paul, Jack, and Jill because Paula is the result and the find first bails out. Unfortunately, though, the minute you turn parallel, what's going to happen? The minute you turn parallel, you actually notice you ask for age of a lot more objects. Well, let's understand this with a little example here. Imagine just before this talk, I was walking around and maybe I left my smartphone on the table. Maybe I left it right there with the third person who's sitting there. Well, here's what I could do. I could say, could you please check if my phone is there? He says, no. Could you please check if my phone is there? He says, no. Could you check if my phone is there? He says, yes. That took me 3 units of time and 3 units of effort. I bothered 3 people and I got the result in 3 units of time. I could do something very different. I could simply yell out in this room and say, hey folks, I don't know if I left my phone someplace, could you please check? Well, what's going to happen now? Everybody is going to check. Who's going to find the result? Of course, him. Well, there's a good news and a bad news. Well, what's the good news? I got it in 1 unit of time. What's the bad news? I bothered everyone in the room. What's the good news? I don't care. And that is exactly how parallel works. Parallel says, I don't care that I'm wasting more resources with the hope of getting the results faster. So which means when you run in parallel, you may actually run more things than you would otherwise, but with the hope of getting the results faster, and that is something you have to be very careful about as well. So that brings us to the end of the first part. Hope you found that useful. When we come back after 15 minutes, I'm going to start on Completable Future. Thank you. All right, let's get started. We're going to talk about the completable futures in this part. So what is completable future? Let's start with that question. We're interested in asynchronous execution. So what does asynchrony really mean in that context? Well, we want to set off a task to run. And while the task is running, what we really are after is non-blocking. So we want to do something without being blocked for execution of certain task. So this is where the non-blocking things come in. We heard of things like non-blocking I/O, and so what does it really mean to be non-blocking? Well, non-blocking simply means you make a method call, but when you make a method call, you don't wait for that method to complete. You don't even wait for that method to really start for all practical purposes. You're on the move, and you continue executing right at that point. So this is where the non-blocking comes in. But on the other hand, the question is, if you're going to do some non-blocking, how do you really get back the results from that particular call? Well, one of the things we have done in the past is to use futures. Let's think about future for just a second. Well, if you're calling a method, and when you call the method, that method is going to run, and eventually it's going to get you back some results, well, immediately the method could give you back a future object on your hand. Well, great. So I have a future object on my hand after I made the call to this method. Now what am I going to do as soon as I get the future? I could do other things, which is a good thing. But when I want the result, I'm going to say future.get. And what happens when you call future.get? You get stuck. That is no future at all, isn't it? So that is very bleak future, in fact. We don't want that kind of future. So that doesn't work really well. Maybe there is a different approach we can take. Hey, wait a minute, let's see what JavaScript did back in time. Well, back in time, JavaScript code used asynchrony using callbacks. Well, if you think callbacks are a good idea, I've got a suggestion for you. Walk next to a JavaScript programmer and utter the word callback, and watch them begin to cry unconsolably because they have learned the pain of callbacks over time. It's just miserable. One of the reasons is that callbacks lack consistency. What I mean by that is when you receive a callback, is the first parameter data or the first parameter error? There is no universal consistency on this. Somebody may use a data versus error. Somebody may use an error versus data. There's no way to tell. it is really hard to compose callbacks. What if I want to call a method and it's going to give me a data using a callback? When the data comes in the callback, I want to call another asynchronous method, which will then send me data through another callback. Now I need a callbacks. There's a very favorite name for it. It's called the callback hell. And that's not a very fun hell to be in. And also, when it comes to callbacks, there's no consistency of dealing with errors. What I mean by that is different from what I said earlier. When you call a method, sometimes the error will be even before the method is ready to really fire the callback. So sometimes the method may explode with an exception. Sometimes you may get the error through the callback. Again, it's really hard to know which one it's going to do. So in general, this is really, really terrible way to do. So what did the JavaScript world do? The JavaScript world moved to using promises. So in JavaScript, we have what are called promises. So what's a promise in JavaScript? In JavaScript, a promise may be in one of three states. It may be in a resolved state, it may be in a rejected state, or it may be a pending state. A pending state is where it's still going to decide whether to reject or resolve. Resolved state is where it has decided to resolve. Reject state is when it's rejected and it's giving you an error. Well, the thing about these three states is two of those states are permanent. Once a promise gets to a resolved state or rejected state, it will never ever change. When it's in a pending state, it might eventually go to a resolved state or to a rejected state. Well, what is really beautiful about this really is a departure from what we have seen in the Streams API, something I didn't quite talk about earlier. And that is, when you deal with the stream, you have a data flow through the stream, which is really nice, isn't it? So you have this flow of data, and as you are processing the stream, everything is going well. But what if something goes wrong? Well, the answer to this in the Streams API can be summed up in two English words. That's called good luck. So essentially, if the stream blows up, you're out of luck. So in other words, exception handling and functional programming are mutually exclusive. You don't do exceptions with functional programming. This is really a bad idea. So in other words, you don't want to treat error as something different. I think the worst thing we have done as programming community is calling exceptions as exceptions. We should have called it normal, because stuff happens and deal with it, right? And instead we said, oh my God, this is an exception, we're going to blow up, which is really not a good thing. So what do? Well, promises do something really well. Promises have two channels of communication. They have what is called the data channel, and they have what is called an error channel. And the data channel carries the data, and the error channel carries the error. Think of this, if you will, like a train track if you want to. So think of this as you have a left track and a right track, or a top track and a bottom track, depending on how you want to look at it. So there are two tracks over here. The way this works beautifully is, if you are dealing with a function call, let's say you are calling a function, and that function says everybody is happy, things are going well, you continue on the data track. When you call a function, something goes wrong, immediately you fall back to the error track, and you are now on the error track. The function you're calling here says, things are not going well, I'm going to blow up. You continue on the error track. This function says, I can recover for you, and we can get better. You then can switch back into the data track, and then you can have a function right here, which can then take you back to the data track, and you can go. So in other words, when you have these functions, imagine going from left to right. You can be on the data track. Everything is going well, you're on the data track. Something goes wrong, you're on the error track. Something still goes wrong, you're on the error track. Something is able to recover it, you're back on the data track, and you can continue. So there is a very clear distinction as to whether you're on the error track or the data track, and you can go back and forth. And as a result, in the end, you're going to get a result back based on whether you have an error or you have a data. So there's a nice clear separation as a flow of logic, and you're not blowing up things, you are still propagating. So in other words, you treat error as another form of data. That's what you're doing. And errors are first class. citizens. So this is one of the beautiful things about this is you're able to treat them as first-class citizens when it comes to promises. And that is one of the distinctive behavior of promises is that you have the data track and error track. If you allow me just to deviate for a second again, this is exactly what reactive streams do as well, except in reactive streams you don't have 2 channels, you have 3 channels. You have the data channel, the error channel, but you also have a completed channel, which is the 3rd channel reactive streams offer. That begs the question then, what's the difference between a reactive stream and a promise? The difference is a promise carries 0 or 1 piece of data ever. So through the promises chain, there's only one transmission. You start from the left and you end up in the right just once. In a reactive stream, it's a stream of data that goes through it. That's the second difference between the two. So promises for 0 or 1 data, stream for 0, 1, or many pieces of data. That's the distinction between those two. So given this, data channel versus error channel, and failures are treated like they are data, and the beauty is they are extremely easy to compose. I know what you're thinking. You're thinking, all right, Venkat, you went at length talk about promises in JavaScript, but I thought we were talking about completable futures. Here comes the real secret. Java has promises. But if they called it promise, you would know it. So they said, we'll call it completable futures. So completable future in Java is nothing but promises in JavaScript. So this is purely the same idea, the same concept. In fact, completable futures are the promises in Java. So the JavaScript promises are now available in Java, which is the form of what are called completable future. So anytime I use the word completable future, I often interchangeably use the word promise because they both are pretty much identical concepts to what they really do. So completable futures are the promises of the Java world. That's what it really is. So completable futures give us the ability to do what we have really learned from JavaScript. I know we are thinking that's kind of scary that we have learned something from JavaScript, but absolutely we want to learn from everywhere we can, and JavaScript has taken the pain over the years to really learn about things. So what you have are what are called stages. So completable future has stages. So what is a stage? Stage is just a pipeline of execution, and you can go from one stage to another stage to another stage in a completable future. What do every single stage do? Every single stage takes a completable future and returns another completable future. There is one thing you need to be very aware of completable future. Completable futures are the villain in a bad movie. It's like Thanos, right? It keeps on coming back. There is no end to it. So if you ever think you can kill completable future, you're going to live forever because you will never be able to do it. So when you call a completable future, what does it give you? Another completable future. And then another one, another one, another one. There is no end to it. It's wise to give up at some point and walk away and do other things in life. That's exactly how completable futures work. So think of this as a very long running train. There are times you get on the train at some point, you get off at a certain station, and you don't worry about where this train actually ends because it may never end. It may keep on going in circles, who knows. That's exactly the whole point is completable futures keep generating other completable futures. There's no end to it. Now, given this, one stage completes for another stage to run and may run. And so how do we really create a completable future? How do we work with it? So I'm going to talk about how to work with this. I'm going to take some silly examples, but nevertheless it illustrates the point about how completable futures actually work. And along the way, we will learn about threads versus completable futures as well. So the first thing I'm going to do here is to bring in java.util.concurrent right here. Let's go ahead and bring up a completable future and play with it. So we'll say over here, let's create a method called create. So we'll say public static completable future, and let's say of integer for lack of better things. Let's say integer, and we'll call it as create. So a very simple little example to begin with. So what am I going to do here? I'll simply say return completable future dot supply async. And in this case, I'm going to keep it extremely simple and trivial. I'm just going to return a value of 2, if you will. That's all I'm going to do. Nothing really exciting. So what does this completable future do? When you call it, it returns a value of 2. Doesn't really do much work. Obviously, you could have returned the true directly, but asynchronously, it's going to return the 2. We'll build upon this a little bit later and work with it. So back over here, what do I want to do? I want to say completable future of integer. We'll call it as future or promise, whatever you want to call it. I'll just call it as future is equal to, we'll call the create method right here. So now that I've created the create method, the question is, how do I really get the data from this and I'm going to use it? Well, I can say future dot, and we can do some work on the future. Well, what am I going to do with the future? Well, maybe all I want to do is to just print the result when I get to it. Before we do that, let's step back for a minute and talk about some famous or popular functional interfaces. So it's really helpful to think about these interfaces in Java 8. And let's think about supplier. Well, remember what supplier is. Supplier of t has a method which is tGet, if you recollect. Then you have a predicate. And what does a predicate really do? A predicate of t actually says, I'm going to have a method Boolean test of t, if you recollect. And then you have a function. And what does a function do? A function simply is going to be t comma r, let's say. And in this case, it has a function that takes a apply function that takes a t and returns a r. And finally, you have a consumer, which is going to be a void accept, which takes a type t. These are I would call as the most popular or famous functional interfaces in Java 8. Let's talk about each of these. Consumer is probably the one you see a lot. Where do you see consumer? You see consumer in pretty much for each. For each uses consumer. What does consumer do? It takes a data and eats it, right? That's all it does. It doesn't return any value. As a comparison, I say consumer is like my government. It always takes my money. I get nothing back from it. That's how I feel about consumer. On the other hand, the polar extreme to this is supplier. Do you notice how kind supplier is? It never takes anything, but always gives you something back. I say it's like the mother's love. You always get something from mother, but never does she want anything back from you. So that is basically a supplier. You see this in factories in general. Wherever you want to create an object, you end up using the supplier. That's where you use this. A predicate, on the other hand, is going to return a Boolean value all the time. So this is used in the filter. So anytime you call the filter method, you're passing the predicate to the filter. And similarly, in the case of a function, you use this in map. Now, clearly, these are candidates from the Stream API. So the question is, why talk about them here? Well, it turns out Completable Future also uses the same interfaces as well. So it's a good idea to really relate them because it becomes easier for us to use the API once we understand the purpose of these interfaces. A consumer is going to simply take away the stuff you give it and return nothing back. Supplier, on the other hand, provides something. Now you know why they called it supply async. The reason they called it supply async is, notice that is a supplier right there. It didn't take any input, but it's returning some value to you. So supply async actually takes a supplier as its input. That's what you're dealing with. But obviously the question is, what do I want to do here with the future? I say future dot, and I want to really print the result I'm getting, which means I'm going to consume the result given to me. When you start thinking this way, the API becomes very intuitive. I want to consume. Now, obviously, what kind of method am I going to use? Well, a for each method doesn't make any sense because remember, a promise only deals with 0 or 1 element, whereas a stream deals with 0, 1, or many elements. So the for each makes sense because when you have many, you say for each. When you have only one, it's for one, not for each. Well, okay, for one doesn't really sound really nicely. Why not simply use the word accept? Because that is the method of the consumer after all. So we could pretty much use these kinds of methods, if you will, for the consumption of this. And so we can say, then accept. Now, why did they use the word then accept? Well, the reason is in JavaScript, promises are called as thenable. So a thenable object simply is an object on which you can call a then method. So they're called thenable. So you can see the historic reasons that it kind of kicking in. So it's a then accept, meaning I have a future object. When the future resolves, then accept the result given by it. So what do I want to do here? Given the data, I want to output the data that I have received from this then, and that's basically what we are trying to do here. And notice it printed the result 2. I know this is a really lousy example. All it did was it print the value 2 from there, but nevertheless helps us to really see the reasoning behind these APIs and interfaces so we can get a really good grip of what these methods really mean. So now you know why it's called then accept. It is a then accept because the word accept because it's a consumer, the word then because after the future resolves, then you want to accept it. It's a thenable. That's why you have the word then. Once you get a grip of this, it becomes easy to see. If you have a then accept, most likely you're going to have a then apply as well, because there are times you want to transform the data and move forward. Now keep in mind, what is the result of then accept? The result of then accept is going to be take a wild guess what it is. A completable future. Remember, there is no completable futures are immortal. It will never die. It keeps on giving. So as a result, this is future 2 that you're going to get from it. But in this case, this is a void and not an integer. And the reason it's a void is your then accept is not returning any data. It's a consumer, so that becomes a completable future of void. And you can do something else with it if you really wanted to. We'll see this in just a few minutes. You saw the result 2 being printed a few minutes ago. Let's go back and rework this a little bit. So I can go to the create method and say .then accept. And what am I going to do? Given a data, I can say output the data that I have received at this time, and I can just print it out as you can see right here. Let's start with that really quickly. Now that you can see that it printed a value of 2. Now you said just a minute ago that returns a completable future. Well, you can then continue further. But obviously here, I cannot say then accept. Guess what? There is nothing to accept because this completable future it returns is one of void. So I can't take a void and do anything with it. Wonder what I can do with nothing given to me. Is there an interface in Java that takes nothing and gives nothing? It's called runnable, isn't it? That's the rudest of all interfaces. It says, I will not listen to you and I will tell you nothing. It's like some stubborn people at work, isn't it? You can't talk to them, you can't get anything out of them either, right? That's runnable. Well, kind of, it gives you a clue. Then the method is going to be called as then run. And what am I going to do here? I'm going to say this never, if I know how to type that, dies. Right? So this is going to be the call following it, this never dies. And if you're not really sure about it, you can just go further and say, really, this never dies, right? And it keeps on going. And this is a good day at work. You want to continue this, you can say, I'm busy coding, right? And you can continue with this, and really, this never dies. And that's what I meant is, there is no end to it. So you never wait for this to finish because completable futures are immortal, right? It is just going to go on. At some point you say, I'm out of here. So that's basically, you just tap onto this train and you get the data and you're out of it. So this is exactly what it is. Now you know why it's called then accept, why this is called then run, because it's a runnable you're going to pass to it. This is a runnable interface. It becomes really intuitive once you really think about the reasons why these things exist. It becomes really easy, intuitive, and then you're able to code it very fluently from that point onwards. So that's basically what we just saw here. Is the completable future. Well, that begs the question then, what about threading? How do these things actually work? So to understand this, let me talk about yet another beautiful feature here. So we created this. How do I get the data from the collection? I actually showed you a better way to get the data, but there is also some bad ways to get the data also. So what you can do here is you can go to the completable future and you can call the get method. Now, there is also another name for the get method. It is also fondly called as bad idea. So this is not a good method to use. Why is it not a good method to use? Well, if you notice over here, I'm going to output over here as get right here, and I'm going to output the result of the get method. What is it going to tell us? First of all, it tells us you should handle exceptions. Well, we are mature Java programmers. We know exactly how to take care of those things. We'll simply throw exception and be done with it, right? That's how we, tell the compiler how we feel about it, right? So in this case, of course, I run the code. It said 2. Now, why is this such a terrible idea? The reason it's a terrible idea is that the get is a blocking call. So that means, for example, if I go out here and say here as an output, now let's go back to this code right here and we could say, let's call it as compute. And what does the compute method do? Let's say the compute method is going to take nothing, of course, but it's going to return the value of 2. Let's say return 2. And in this case, I'm going to say sleep for about a second. So I'm going to take a little nap here for about 1 second. And so let's provide the sleep method right here. So this is going to call the compute method, which is going to take a little nap and return a 2. And what does the get method actually do? Well, remember, this is going to run asynchronously, but the get is going to block on us. So if I go back and run the code this time and see what the output looks like, notice we are waiting, and then it said here. So that is an example of where we are actually being blocked. In fact, let me go ahead and write this a little differently. Completable future integer future is equal to create, and then I'm going to say over here, got it, and then I'm going to call the future.get. And then, of course, as you can see here, when I run this code, it says got it, but you're blocked until the result 2, and then you go here. This is why get is a really bad idea. So I have only one recommendation about get. The best thing to do with get is to forget. So don't even bother, right? Really bad idea. Don't use this method. I would encourage you to use the then accept rather than using get. Don't even bother using get. So this is not a very smart call to make because it is a blocking call, and you don't want to do blocking because it kind of defeats the whole purpose of asynchrony when you block on stuff and wait for it. So that's one of the things. There is an alternative to this, which is called the get now. A get now is an impatient call. So a get now over here says, I'm going to specify a 0, if you will. So what does the get now do? A get now says, if the completable future has resolved, get me the result of the completable future. If it has not resolved yet, I don't care to wait on it. Just give me a 0. So this is going to be in a hurry, and it just wants to keep moving. So when I run this code, notice you got a 0 right away because the completable future is not done yet. And if it's not done, give me a 0. So it's non-blocking, but unfortunately, of course, it's impatient as well. It's going to give you the result right away rather than waiting on it. If I remove the sleep, on the other hand, and run the same exact code, you can see that, well, actually, it doesn't because it's still taking a little while to run. But on the other hand, if I were to delay this just a little bit, sleep for about 100 milliseconds with the hope that it'll be done by then, maybe we will get that value too right there. Absolutely. So again, I'm not a big fan of get now. Maybe there's some special situations where it might be useful, but in general, I would say don't bother with it. Well, that brings up the question, what about threads of execution? Where are things going to run? To answer that question, let's look at this a little differently. Notice I don't have a sleep right now. And I come back over here. In the main method, I'm going to say in main, and I'm going to say thread.current thread. So obvious that's going to be in the main thread. Then I call the create method. Then I say dot run, so then accept. And in this case, I get a data, and I'll call it as print it and pass the data to it to print it. So that is my code at the moment. Now the question is, if I go to the over here and say public static void, and let's call it as print it, and what am I doing in the print it method? I'm going to get a value, and I'm going to simply print the value. Let's take baby steps and run this. So when I execute this little code now, you will notice that it said main thread is running it, the value of 2, no big deal. But the question really is, what is your thread of execution? I do have to say this is something I really love what they have done. The point here is you don't want to do more threads for no good reason. So here's the beauty. The question really is Completable Future running in a different thread all the time? Is the print running in a different thread all the time? If you have done C# programming, C# had asynchrony for a while now, and this is exactly how C# behaves as well, which is really nice when the implementation is sensitive to not having to switch threads unnecessarily. So to understand this, let's go back to this example, and let's print out the thread of execution in the compute method. So in the compute method, I'm going to say compute, and then I will say thread.current thread to show what thread is executing the compute method. Similarly, I am going to come down to the print method, and I'm going to print the value, but after printing the value, I will also print here thread.current thread. Before we go further, let's make a quick observation. Notice that we got the completable future on our hand here. So we'll say completable future of integer over here. So integer. And let's say future is equal to. And I want to make this extremely clear so we don't have any confusion about it. So let's go ahead and say sleep of 100 milliseconds. And then I call the then accept. Let's understand a few details now. Notice that I first call the create method. When I call the create method, we step into the create, it runs this piece of code, it returns a value of 2, and once it returns a value of 2, that's going to run asynchronously, sure. Then, immediately it returns a value of 2, which means by the time you get out of the sleep, the completable future has already completed. Now, you go to the completable future, which has completed, and you say, then accept, and the completable future says, you know what, I am done. I'm not going to wait for you because I'm already completed. And as a result, I will let you do the work. So this execution is going to be in the main thread because the data is ready and available by the time you call this method. In other words, when you call the then accepted, the main says, hey, look, the data is already available. I don't have to switch to another thread. I might as well execute this in the main thread. Is that really true? Let's find out right here. So when I run this code, the main prints main, the compute prints the thread in which it ran, which is in the common pool thread. But did you notice the print actually is in the main thread? And the reason the print is in the main thread is because when the main is calling then accept, the future has already completed, the completable future has already completed, and it doesn't have to switch to another thread unnecessarily. It immediately runs it in the main thread. On the other hand, let's go back to this code right here and introduce 1,000. Now, a sleep of 1,000. Now you know that by the time I finish the sleep, the completable future is not completed yet. So when I come and call the then accept, what does the main say? The main says, well, I'm not going to wait around for you to finish. I don't know when you will finish. You may never finish, who knows? So I'm going to be non-blocking, and the main goes away. So in this case, if I said here, right here, one more time, apologize. Let's go ahead and comment this out. As you would expect in this case, when I run this code, you will see the here being printed after the 2, absolutely. But when I put the sleep in place, by the time I get in here, the completable future is not completed. So the main says, hey, you take care of this. I'm not going to block, and prints out here and walks away. What about the other thread that eventually finishes its work, returns the value of 2, and when it finishes that, it says, oh, look, I actually have some more work to do in my pipeline. My completable future is piping with another completable future, and I might as well run the train. So this print it now is no longer going to run in main, because at this point, it can run in the other thread when the computation is going to finish. Is that really true? Let's run the code and take a look at it. And notice at this time, the compute was called, well, okay, maybe I should really put a little sleep here to prove the point. Let's go ahead and sleep for about a second right here. Now when I go back and run the code this time, you notice right there, notice the thread that's running the printed is different from the thread that ran it here. So the moral of the story here is, just because you're looking at this execution, doesn't mean you know exactly the thread that's executing. In other words, think of the thread as an implementation detail. It shouldn't be your concern. So in other words, this code that you are calling right here in the then accept may run in the main thread if all the execution is already done by the time you get to that point, or it may run in a completely different thread if that execution is not done, and as a result you're non-blocking. So the point really is, you're not going to block on it and wait on it. You're just going to continue with that and keep processing it depending on the state of the completable future at that particular time. And that's exactly what we just saw here, is how the thread of execution actually differs. Now that begs the question, we saw this executing in the fork join pool, the common pool, as you just saw here. Again, going back to this example, let's remove the sleep for a second. And if we run the code we just saw here, you will notice that in this case, that the execution of compute is in the common pool. That's where it's executing. Oh, wait a minute, what if I don't want this to run in a common pool? What do I do in that case? Well, then what you could do here is, when you are creating this, you can say, for example, fork join pool, and you could create a fork join pool right here, and we'll call it as pool is equal to new fork join pool. And once I create a pool, I can specify the pool as a second argument to the supply async. And this says, run this asynchronous job in a thread from that pool and not from the common pool. So you can specify that as well. If that is something you want to do and control, you can certainly do that as well. So you can vary the pool in which the code is going to execute. I also talked about async versus non-asynchronous. You have versions to go back and forth depending on how you want to do. That brings up to the methods that we really want to talk about. So the methods I want to talk about here is the then accept method. So what does the then accept method do? The then accept method is really a consumer. It accepts the data, and what does it return? It returns a completable future of void to continue with your work. Why would you want to really deal with the completable future of void? Imagine you are trying to perform a database operation. Maybe you want to perform a commit. Maybe you want to write to a log file. Well, when you're done with the operation, you want to send a message saying, I've committed to the database. Or you want to display an error if something went wrong in committing. Or maybe you're logging something and you want to display a message saying you've logged it. Or maybe you want to send the data to a remote server, and when you're done with sending the data, if there was no error, you want to celebrate that and report that everything went well. Or if there was an error, maybe you want to report that there was an error. So in other words, the one that has a then accept returns a completable future of void, but that contains information about success or failure, and you can decide what to do with it. And this is one of the reasons why you really have that ability to continue further. So jokes aside, there's a really good reason for why this is a good idea. So create and then accept. And then in this case, of course, given a piece of data, I want to output the data. Well, in this case, of course, it's going to print the data as you expect. It printed the data. Let's get rid of the thread information right now. And this time, of course, let's go ahead and remove this thread information also. So you will notice that in this case, it printed the data right there, the value 2, at the very end when we printed it. But if this was committing to a database or sending the data to a remote server, you want to say that, yep, that really went well. Then you say, then run. And at this point, you can simply say output, and you can say that went well. And then you can print that result or do whatever you want to do to celebrate the success of that operation. That is the reason why you have this continue further, is because you want to make sure that the operation you performed here, like writing to a database or sending to a remote server, was actually successful, and you want to report that maybe. That's the reason for the then accept. And that really is useful to continue further with the processing to say that last step I did, a terminal operation I did, was actually really successful. That is the then accept. So I also talked about the then run, which is the purpose of that is to kind of say, yep, that previous operation actually worked really well. What about then apply? So here's a way for us to think about it. If you want to think about this a little differently, let's do a little map of this right here between stream and, let's say, a completable future. Now, first of all, remember, this is 0, 1, or more data. This is 0 or 1 alone, right? That's one of the differences between the two. The second is only data channel. This contains two things. You have a data channel and an error channel, right? So you have two channels of operation between these two guys. That's another difference. However, you have a function called map over here. Well, for each over here. What is kind of the equivalent of that? We saw this already, and that is the then. It's called the then accept. So the word accept comes from the consumer interfaces, then accept. That's what we are using really at this point. Similarly, you have a function called the map in the case of stream. Now, what is the equivalent of, remember what map does? Map performs transformation. Map transforms one stream to another stream. Well, you know what? They could have called it map here as well. But if they did, then we would understand it very quickly. So like, no, we should really give a different name for it. So this is called then, what is it called? This is going to be apply. So then apply is like your map, if you will. So what does the then apply do? It performs transformation. It transforms the data you get from one completable future into another completable future. So they're pretty equivalent. So in my mind, every time I think of then apply, I think of a map because it's a transformation I'm really doing. That's my intention here. So just like they used map in optional, they could have used a map here as well, because all you're doing is performing the mapping operation, right? That's what it really is. But once you get a hang of it, it becomes easier to work with it. That's the then apply. So what am I going to do here? Let's go back to this example now and notice right here, remember my little example is returning a value of 2. That's what it's returning. Then I say dot then over here accept. And what am I going to do? Given a piece of data, send me data times 10. We know that 2 times 10 is 20. So when I execute the code this time, what is it going to do? Oh, this is complaining bad return type for the lambda expression, a missing return value. Let's see what I did wrong here. I then apply. I said apply, but I typed accept. A little error on my part. So then apply, and this is a lambda that's going to return the result for us. When I run this notice, it said 20 because 2 times 10 is 20. So we perform the transformation on line number 20. That's what we just did. So line 20 says I'm going to perform a mapping operation where I'm receiving this data, I'm converting it to a times 20. Keep in mind, this is returning a completable future of integer. This is returning a completable future of integer as well. This is returning a completable future of void. On the other hand, if I set 10.0, then this is returning a completable future of double, and this is taking completable future of double as well, and as a result, a consumer of double, and it becomes a 20.0. So because we are not using type, the type inference is your friend here. Had I written the code like this, if I had said over here, integer right here, and integer, and if I had written the code like this, you can see it's 20. If I said 10.0 right now, I get a compilation error because this returns a completable future of double. This wants an integer. We have a type incompatibility problem. Because I did not use that, because I used type inference, it rolled over to the right type properly for us. In this case, type inference actually helped us. But if you were to really provide the type in your code, you would have to really deal with it depending on what you're trying to do with this operation, or if this was specific to one type versus the other. So this gives you a nice pipeline. Oh, that's another point, is both of them have a pipeline, right? So both of them are going to provide the pipeline for you. The stream provides a pipeline. The completable future also provides a pipeline for you. That's a nice little pipeline in both of those cases. You can also say the stream is lazy And so is this guy right here. It is not going to eagerly evaluate all of them right away. They both are going to be lazy as time goes on. You're going to execute when things are available. So there is a similarities between them as well, and differences also, as we can see right here. So that is basically what we are looking at in terms of how these two are relating to each other. So we saw this pipeline, but what about creating a pipeline and then completing? Well, in the examples I created so far, it's a little bit of an unfortunate example because this guy is actually completing it. But there are times when you want to create a pipeline, but you don't want to complete the pipeline until much later. You want to come back and complete the pipeline where you build a pipeline and then you perform the computation elsewhere, and then you push the data through the pipeline. That would be really nice. In this example, the mouth of the completable future is the data source. But I don't want that all the time. I want to create a complete different pipeline and then come back and push the data through the pipeline. That would be really nice. How do we do that? And that's what I'm going to do now, is to create an example where we can create a pipeline first, and then we want to push the data through the pipeline. So what are we going to do now? So what I want to do here is completable future of integer. We'll create a little integer right here, integer. We'll call it as future is equal to new completable future. So we'll create a completable future object right here. So we created a completable future. What's our next step right now? Well, once we created this completable future, let's go ahead and say dot then apply. And given a data, I want to say data times 2. So I'm asking it to continue with this pipeline where I am going to then build a pipeline of a transformation. Then I say then apply. Given a piece of data, I want to increment the data. So I could go through the pipeline and do various operations. For example, this might be calling one function in your library, which is going to return a result, and then you could do another function based on that result, and you can draw this pipeline of transformations in your code the way you really want to do this. So you could go ahead and build this up as much as you want to, depending on what you're trying to really do. At this point, let's say that's all I want to do with this pipeline. Then what am I going to do? I'll simply say build the pipeline. So this is my very first step. I just built the pipeline. That's all I'm doing at this point. Nothing really exciting beyond that. Let's see what I'm doing here. This is going to be of integer because the type is going to be a completable feature of integer. What happened there is you're having a little issue with the type inference. Type inference works most of the time, except when it doesn't. So when it doesn't work, I usually throw the type at the time and I keep moving forward. So in this case, of course, when you don't provide the type, it says, I don't know what the type is. I got to look at my surrounding to find it. And this guy is not very helpful. It says, my type is the exact one as you give me. You're like, that's very helpful. Thank you. So I'll just go ahead and put the type in this. That's where the type inference really doesn't work really because it's not enough context to determine that. So now we said it's an integer and it says build the pipeline. Oh, we built the pipeline, but are we running through the pipeline? Not yet. So what am I going to do then? I'm going to say future dot then accept. And what am I going to do? Take the data and I'm going to output the data right here. So this is going to output the data. So we will say prepared. Let's say prepared to print. Again, you will notice that in this case, we don't have the pipeline active yet. It doesn't matter how long we're going to wait right now. If I wait for a second, it's just going to wait for a second and print that result. It's print the result and wait for a second. It's not going to do anything. Why? Because we built the pipeline, but no data was actually passed through this pipeline. This is like some places where I've seen railway tracks laid down, but they lost the funding, so no train ever went through the tracks. That's kind of like the place here, right? So we built the pipeline, but nothing really went through it. So what am I going to do then? Well, after a second delay, I'm going to say future dot, and what am I going to say now? Complete. And I'm going to pass the data through this complete. I could take my sweet time to go do this operation elsewhere. It doesn't have to be in the main. It could be somewhere else. I could put it in a completely different thread, whatever that could be. Or more important, you could be building a pipeline and pass it to somebody else, and they could be holding onto the pipeline and send the data back to you. And when the data arrives to you, you can do other operations with it. Let's send a 2 as a complete right now. So what does that really do when you send a complete 2? Well, let's think about it. I take the value 2, double it. 2 times 2 is 4. I increment it, becomes a 5, and I want to print the value of 5 when everything is said and done on the complete. So let's see if that's actually going to work. So I run this code now. Notice it says build the pipeline. Oh, wait a minute, it said 2. A little glitch here we have to be very careful about. Notice that I connected this to the future. Well, this future is taking this pipeline of data and it's going to transform this. Let's be a bit careful about it. Let's save that away. Let's build the pipeline right here with the future. So I want to transform this. So future dot, and then we will put this last call to that one. So let's go ahead and apply this, and we will say dot then accept. And in this case, let's make sure we are putting it the right place. So this is the pipeline we drew at this point. So we created the pipeline, rather than built it, we'll say created a future. We prepared to print or build the pipeline, let's put it that right here. So we build the pipeline, but we take a little nap right here, and then we call the complete on this particular future and pass the data. Let's see what's going to happen this time around. So we want the result of a 5 to be printed, isn't it? So right there it says 5. So what's going on here? So we took the future that got created right here. On that initial future, we are completing the call to it. And then this pipeline applies the transformation and prints it. You got to be careful where you connect to, because the result of this, you're appending to that and you are printing this out. And then, of course, we complete the future, pushing the data through the pipeline. So where this is really useful is you can draw the pipeline, send the pipeline off and say, hey, go ahead and complete this work. When you're done, push the data to me. I'll receive it and process it. So this is an example of where you're creating the pipeline and completing it. On the other hand, how do I tell that something really went wrong? Now, this is where we need to step back and ask how this is going to be processed. Now, remember, when it comes to exceptions, what about exception? The short answer for that is oops, right? So we don't really deal with it. This is not going to work really well with streams. We don't want to ever talk about exceptions when it comes to streams. It doesn't really handle it very well. What about completable future? Well, this one, he is going to handle that fairly well by having the error channel. So the error channel is saying, when something were to go wrong, I will deal with it in my error channel. But the way this works actually is by having these two different parallel channels, if you will. If things are going well, you're on the right path. If things are not going well, you're on the left path, let's say, and then you cross over depending on you have an error or you recover from the error, and you can go back and forth and you keep progressing in your pipeline. And that is something that we need to really get comfortable with when it comes to dealing with how we are going to work with it. So to understand this, let's step back and take a look at another example, and we'll come back and work with this current example after that. So I'll save this away. Let's go back to a previous example we just created, and just to fall back on how this is going to work. And then I'll come back to this example right after that. So let's say over here I have a compute method, which is going to take no input, of course, and all it's doing is returning a 2. So we'll just start with the same example as we did before, but then I'm going to start with a static method. We'll call it as Completable Future, and in this case we will say create. And what does the create method really do right here? The create method says, I'm going to return a completable future.supply async, and in this case we will say, just call the compute method. Okay, so that's going to simply return the result of whatever the compute is returning. But back over here, I'm going to call create and simply say dot then accept. And in this case, given the data, I want to output the data. Well, let's start with baby steps right now. So all this is going to be doing is simply print out the value that this is going to return. And so as a result, it printed a value of 2. We can even transform like we did before. We could say dot then apply, and we can say given a piece of data, we can say return data times 2. Okay, so that's really giving us a 4. However, what we can then do is to ask it to deal with errors when that happens. So what do we do about exceptions? What if something were to blow up? What are we going to do about it? Well, this is where we need to get comfortable with the way this API works. When you have a completable future, if things are going well, it is going to find out for you the very immediate, let's go to the completable future real quick. So we'll say completable future, let's say Java, and we'll ask for the completable future. Now, if everything is going well, you are going to be working with the then methods. So in other words, think of the then methods right here. So the then methods, let's ask for then. So the then methods really are useful when things are really going well. Let's say then accept. So all these guys, the then accept and then accept, then apply, all of these are success methods. If everything is going well, you stay with this then method. So in other words, when a completable future succeeds or resolves, you go to the nearest then method. That's your idea right now. But on the other hand, what if something did not go really well? What are you going to do about it? Well, then you are going to hit a method called exceptionally. And the exceptionally, I really don't like this word. Exceptionally simply is a catch. That's what you're really doing. So this says, if something were to go wrong, I will get to the exceptionally method, and I will deal with that at that particular point. So that is basically what the exceptionally method is interested in doing, is to handle the error. But the way this works is something we need to be careful about. So I'm going to go back over here and say dot exceptionally. And what am I going to do with this exceptionally? If you look at the exceptionally, notice that it takes a function that takes a throwable as an input. And in this case, it takes a throwable as an input, and it is an extends of type T, whatever that is going to return. That's up to you what you want to return from that. But all I'm going to do is simply say throwable right now. So throwable. And what do I want to do within here? I'm going to, first of all, let's call it as handle exception, and I will pass the throwable to it. So what am I going to do in the handle exception? Well, in the handle exception, let's try this. So public static, let's say void handle exception. This is going to be a throwable, so throwable. And in this example, all I'm going to do is output the throwable. Maybe play a sad music, say that something really went wrong. Then what am I going to do? I'm going to say throw new runtime exception, and I'm going to simply say it is beyond any recovery, right? So it's beyond hope. Let's just put it that way. Beyond all hope. So essentially, we're going to just blow up at this point with the exception at this point and say, I'm going to throw this out as an exception. We'll see why that's being done here in a little bit. And that's what this is going to do, is to just blow up at this point, and we'll resolve through the compiler errors if we get any. Well, right there, it says bad return type for the lambda. What are you going to return really? Okay, I'll say integer for now and see if it's happy with it. It says it wants a void. Fine, we'll give a void right now and run through it. Okay, so it printed a 4. But what is this really heading towards? Notice in this example, our compute method returned a true. That resolved the completable future. And because it resolved the completable future, we came to the nearest then, which is transforming it 2 to 4. And the next nearest then is printing the 4, and that's the result we got. However, if I go back over here and say throw new runtime exception, and we will say, just like we get on real projects, we get an exception called something went wrong, right? Very useful messages that we normally get. So it says something went wrong and blows up. Now what's going to happen? Well, remember, our completable future did not finish successfully. It didn't resolve, it rejected. And because it rejected, what is this completable future going to do? It is going to seek the nearest exceptionally and bypass all the then apply. Am I making sense? So when you look at this pipeline in front of you, there are two candidates in front of you. There are the then functions in front of you. There are exceptionally functions in front of you. And when something is good, you find the nearest then. If something failed, you find the nearest exceptionally. So that is how it's going to jump over in terms of where it's going to go. So if everything is good, you are in the then apply. If something is not good, you skip the then apply and then accept, and you're going to hit the exceptionally because that's the nearest path you can jump over to complain about it. Well, in this case, of course, I could specify where to go based on what really happened. Well, this is saying unreachable on return 2. Let's see where the return 2 is. Of course, I couldn't put return 2 right there. That doesn't really make sense to have it. So what just happened over here? Let's go ahead and run the code and see what the result says. Notice it says completable future exception, runtime exception, something went wrong. Well, actually, in this case, because this is an exception we're going to handle, let's put that right here as well. Well, in this case, this guy is saying, okay, so it's a little bit of a pickle here, because this guy, what is he returning in the exceptionally block? Let me see where the exceptionally is. Handle exception. This guy wants to return a void. Let's see how this is going to go. So this is going to return whatever the type is. I'm going to just say a type T for now, so that I can make it very generic. So this is a static type T. Whatever the type T is going to return, I don't really care about it. And then that's going to be the handle exception for it. Oh, let's see. How do I write this one? So this is going to be public. Is it before T? So T static. It doesn't have a type, so that's a T. Whatever it's going to throw as a result back to the caller. So that's going to be, right, T over here, not on the other side. So that's going to be the return type of T as well. So what happened? Illegal startup expression, then accept. This guy is not too happy. Why? Because this is supposed to return a T value, so he's not too happy. All right, let me step back here. So let's take baby steps on this one. So let's go back to this guy. Let him return an integer because that's a chain we are dealing with. Exceptionally, let's see what it's going to do. So this is exceptionally. This is going to return, of course, the integer value. And I'm still struggling to get the exception out of this. When it fails, that should have really hit the exception block right here. Let's see why that did not hit to the exception block. So what am I doing here? Oh, I'm printing the throwable. Sorry. This is going to be my fault. I should say oops, and then, or let's say error. Maybe that'll give us a little bit more context as to where we are getting that. Maybe that's why I was getting confused right there. Let's give it a try again. So run this. Oh, there we go. So that says error. So let's revert back to what I had a minute ago. Let's simply say, let's move this to down here for a second. So let's then say that is going to be exceptionally, and let's make this a void method for now. Let's see if that gives us the result we are looking for. There we go. Apologize. That's what it was doing the correct thing, but I was getting confused because I didn't see the display of the error from this method. So notice it says error, and then it says throwable, which is the error we got over here from the other call, but that one is the error that we are displaying. So what's going on? Like I mentioned earlier, it finds the nearest exceptionally block to go to. But you can also recover from these kinds of exceptions as well. So let's give this a try again. Let's say in here, I am going to provide an exceptionally right here. And in this case, we will say handle exception 2. So what does handle exception 2 do for us? Now, in the handle exception 2, I am going to say handle exception 2, but I print out the error, but I return a -1 for whatever reason. Well, now what's going to happen? Well, let's follow through this again. We are calling the create. The create says, I'm going to blow up. Let's find the nearest exceptionally. Well, what does that do? It says, I'm going to print the message over here, but I will recover from this. And I've handled the exception. I want to return a -1. Now, you were in the right track. You went to the left track. The left track says, I've recovered back, and you're back on the right track. As a result, when you come out of this exceptionally, you're going to go to the nearest then accept at that point, because you have recovered from the error. So that should print out a -1 as an output if everything were to go well. Let's see if that's actually true. So when I go back and execute this code, oh, wait a minute. The semicolon, let's remove that semicolon right there. So when I go back to the code and execute it, all right, this is going to be an int, isn't it? Type. So where's the handle 2? That's going to be an int, which is what I want to return. So fire away. Now notice it printed a -1, and the reason for that is it printed an error, something went wrong, but it still printed a -1. Why? Because this guy recovered from the error. And because it recovered from the error, at this time it says, I am going to go to the nearest then because this guy recovered from it. So the moral of the story is, in your exception handler, if you don't blow up, that means you are recovering from the exception. If you blow up, you're saying continue on the error path because this is beyond repair. If you don't return an exception, if you don't throw an exception, but you return a normal value, then you switch back to the data path, and then you're going to continue on the data chain. So that diagram I drew a while ago, where I showed you how these things are going to behave. So you have a function, it returns the data, you keep going on this path. But anytime something goes wrong, then you are going to jump over to the error track. And now on this one, you're going to go through a function again. If this blows up, you stay on the error track. If this returns back a good result, then you are back on the data track and you go this way. So it depends on, these are your exceptional. So this is exceptionals, and then this is, of course, the thens, right? So it depends on whether you have the data being returned or you have the error being returned, and you go back and forth depending on how you process this chain. That is something you got to get comfortable with. So think of this as 2 tracks, and you go back and forth between the tracks depending on what you are doing. If you're recovering, you go back to the top track. If you're failing, you go back to the bottom track. So this is, of course, exceptionals. And of course, in this case, you're saying blow up, right? So this is blow up. If you don't blow up, you will go up, right? This is where you are returning a result. This is where you are blowing up. So this is where you are returning. So it depends on where you are in the chain. So this is returning, so you continue on that path. This is blowing up, so you come down. This is blowing up, you continue. You return, you go up. And then, of course, here you return as well, and then you continue right after that. So that's basically how this works. Oops, let me put a return right here. So this is return, and then you continue on that path of execution. So this returns, you are on the track. This returns, you're on the track. This blows up, you're down here. This blows up, you're down here. It returns, you go up, and then everybody is happy, you keep going that. So it depends on which path you are going through. So when you build your pipeline, you're going to build them with the pair of functions, the then functions versus exception functions, and then you carry through. So far, so good? Well, let's then switch over to our previous example. So the one I had created earlier, where we created a pipeline and we are working through it. So what am I doing in this example? Well, what I'm doing here is we created a pipeline right here. So we created a future, and then we said then apply, then accept, and then, of course, we built a pipeline, and then we come here and say complete with the 2. Now, what about exception handling in here? So what I'm going to do here is to say dot exceptionally, and exceptionally what? I'm going to say a throwable, and I will call this as handle exception. And what am I going to do now? Well, in this case, I'll pass the throwable to it. What does this handle exception do for me? Well, I'll say public static. This is going to be an int, a handle exception. This is going to become the throwable, and that becomes the throwable that I'm going to pass to it. And all I'm going to do here is to simply say output error colon. We'll print the throwable, but then we'll return, let's say, a 0. So I'm just going to say I recovered from it. I'm going to return a 0. I'm going to move on. So that is going to return a 0 when something went wrong. 0 plus 1 is going to be 1, and that's going to print a 1 if exception were to happen. When I run this code, what's it going to do? Well, there's no error right now. So as a result, this guy here, completed with the 2, So we went to the nearest then. 2 times 2 is 4. We went to a nearest then. 4 plus 1 is 5. Well, we print 5, the nearest then. So the result is a 5, as you would expect. However, how do I blow up? How do I say something really went wrong? How do I communicate an error? Well, for that you use another function. I'm not happy with this function name at all. It's called completed. This is called complete exceptionally. Now, this is a really ugly name in my opinion. So you can use this on your projects. The boss comes to you and says, how's the project going? I complete exceptionally, right? Which means we totally failed. Well, that's what complete exceptionally is, isn't it? So I always say this among programmers because they know what I'm talking about. The boss doesn't know this. It's always fun. How's it going? Complete exceptionally, right? So that's a nice way to say it. Well, the programmers know what you're talking about. So the point really is complete exceptionally, and I'm going to blow up at this point. So what am I going to communicate to complete exceptionally? Well, I'm going to pass a throwable to it. So in this case, I'm going to say new runtime exception. And at this point, I'm going to say, don't tell the boss, right? So, this is basically the exception that we're going to blow up and send a complete exceptionally. Well, what is it going to do now? Well, in this case, we are passing through the pipeline complete exceptionally. This will not be executed. It goes to the exceptionally block, which prints that result, don't tell the boss, and then returns a 0. And of course, 0 plus 1 is 1. And then, of course, we're going to print the 1 value when everything is said and done. So let's go back and see if that actually is true. Let's make sure we save this and run the code. And what does it do now? Build the pipeline. And notice it says error, don't tell the boss, and returns a 1 instead of a 5. So we can see how we could work through this. For example, if, let's say, math.random is greater than 0.5, we could send that over there. Otherwise, we could say else future.complete, and in this case, we'll send a value of 2. So we could go either way depending on execution, depending on the context, we wouldn't know. So you can see that it failed, and over here it failed as well. Let's try this one more time. Okay, so that's not working really well. So it wants to keep failing for more reasons than succeeding. I'll try one more time, otherwise we'll move on to do something else. Well, let's try this. Let's give it a less chance to fail, 0.25%. Well, actually, no, 75%, right? So less chance to fail. Let's try this one more time. Okay, I give up. Okay, so it's bent on failing. All right, there you go. So that's an example of how you could decide to handle failures versus success, and you can either complete it or you can complete exceptionally and send the data through your pipeline. So again, coming back to this, the way this works really is through this pipeline of operations where you can trigger this evaluation and go through the then or the exception block, and then you can recover from this and move forward. So that becomes a really nice way to do this, and we saw the chaining of this. However, there is one other problem, unfortunately. In Java 8, this is more or less what we had in Java 8. But there is one problem in this code, and that is, let's go back to this code for a second. If we were to run this code without this last part, and what's going to happen now? Well, notice we have a pipeline in front of us. We execute the code, we build the pipeline, but as time goes on, what's going to happen at the very end? Well, I'm going to say done over here. Well, but the problem is nobody really triggered the pipeline. And as a result in this example, when you run through this, if the pipeline was never evaluated, well, how do you know how long you're going to wait for a result to be received? Well, the problem really is this pipeline is never evaluated because the completable future is in a state of pending. Well, remember there are 3 states for a completable future. What are the 3 states? A pending state is one state, then a resolved state, and then a third is a rejected state. Now, if you were to create a completable future at the source, you can reject it right away, or you can resolve it right away, or you could put it in a completely different thread and say, I'll come back and resolve or reject later. But the biggest problem with this is, how long are you going to be in the pending state? Well, that's really an answer you have to ask. There is one thing I recommend very, very thoroughly for people, and that is both in life and programming, never do something without timeout. This is what I tell everyone, especially young people. If you're going to look for love, never look for indefinitely. That's the easiest way to die old and alone. So you time out, right? You say, I'm going to work for a little while, but I'm going to settle down after that. That's just my recommendation, personal recommendation. So both in life and programming, never do something without a timeout. Just for healthy living, right? So you always time out, especially in programming. That's even more important than life. So always do with the timeout. Well, unfortunately, there was no timeout in Java 8. Well, they cured the problem in Java 9. So in Java 9, we have two methods that are available for us. So going back to this example, clearly, I am not really resolving this. It's going to end up in a pending state for a very long time. So what do you do about it? Well, in this case, what I'm going to do is after a second delay, I am going to then say, well, over here, I'm going to say, in this example, well, we will say future dot, and I'm going to say complete on timeout. So this is a method where I'm going to ask it to complete successfully, but if it is on timeout. Real quick, I'm in the Java 8 API right here, and if I look for timeout, notice there's really no method with timeout. The get with timeout, but we know get is really ugly. We don't want to do this. So let me switch over to Java 9 right here in the API. And now I look for the word timeout right now. And notice at this time, I have a complete on timeout. That's the API added in Java 9. You didn't see this a second ago in Java 8. That's a complete on timeout. So I'm going to say complete on timeout. And what am I going to return at this point? I'm going to send a -1. But how long am I going to wait for timeout? You can specify a time and a time unit for it. So you can specify here, I'm going to give a 1 second, a time unit dot seconds, and I'm going to give you a second to finish. If you don't finish in a second, I'm going to then resolve it with the -1. That's what I'm saying here, right? And I'm not suggesting that's the right thing to do or the wrong thing to do. That's what the API gives you. Depends on your problem at hand. You can say, I'm going to wait for this task to finish for a while. If it doesn't finish, I'm going to use this response and move forward because it makes sense in my application. So this is basically saying, timeout with a -1 at that point and resolve it with that result. So what is it going to do then? Well, notice I said a 1 second delay. Well, okay, let's actually say a 2 second delay, if you will. So in this case, I'm giving it a 2 seconds of delay. So I'm waiting for a second and another 2 seconds before I finish it. Let's see how this is going to work. So I run this code. Notice a little time goes away. It gave you a -1 because 1 second later, nothing was resolved. It gave us that -1. When it gave a -1, what happened? -1 came through here. Actually, did it work properly? Well, complete on timeout with a -1. And the -1 should have actually come through here. And -1 times 2 is -2. +1 is -1. Tricky example. That's why it was a -1, isn't it? Okay, so I was losing faith in my own code right now, but you know exactly why it did that. Okay, let's just put it as a 0 blatantly so we can know that's going to be 0 times 2 is 0, 0 plus 1 is 1. Okay, that should really come back as a 1 because we didn't resolve it. Okay, great. So that's basically the response we saw. However, notice that at the end of a 1 second delay, I go to the future and I say complete with the value of 2. Now this time, even though I said complete on timeout, remember one thing important to keep in mind about completable future is that a completable future is in a pending state or is in a resolved state or it's in a rejected state. But remember, these are final states. Once you resolve or you reject, you can never change it. So which means if you complete it successfully, then you're not going to really have, this becomes a no-op. You cannot resolve the resolved completable future. You cannot resolve a rejected future and vice versa. So because it's been resolved right here, this will have no effect on it, which is a good news. So if I run this code now, we're passing a 2 at the end of the time. Oops, complete, not compute. So this is complete. So as a result, if you notice over here, when the 1 second is over, notice that we got a 5 as a value, not the -1. But of course, if this does not complete in that duration of time, then of course we get a 0 or a 1 rather as an output. So that's basically where it steps in if it did not really finish. In a similar way, what you can also do is you can tell him, hey, if the result, it did not resolve on time, I don't want to give you a substituted value, I do want to blow up. And that is something you can do by simply saying R timeout. So R timeout, what does that do? It simply says, if you did not finish on time, I want to blow up to tell you that you did not finish on time, and I want you to do the error processing at that point. So in this case, we are saying R timeout, no data obviously because I want to fail at this point, and you're giving it a 2 seconds delay with the R timeout. Now when I go back and execute the code, a second later I'm completing it. As a result, you got a value of 5. It resolved it, so it will never reject it at that point. On the other hand, if I do not complete in that duration of time in the 2 seconds period, then when I run this code this time, notice that it blows up and it says error and concurrent timeout exception. And then it says that I had an exception. Remember, when you had a timeout, it returns a 0. As a result, you got a 1. We recovered from that at that point. But the essential point here is we are blowing up. So those are 2 new methods added in Java 9. And Java 9 introduced the timeout, complete on timeout, and R timeout. They didn't say exceptionally on timeout, but in this case, it's just R timeout. So complete on timeout lets you resolve at the end of timeout. R timeout lets you blow up on timeout. And then afterwards, it goes to the same chain of evaluation through either handling errors or going to the then. The same rules apply that we talked about earlier. So we talked about succeed on timeout. We talked about fail on timeout. So far, so good. Then comes 2 methods. And at least when I looked at them, I got pretty confused. Combine and compose. What does it really mean? Combine and compose. Well, keep in mind, Java is statically typed. JavaScript is dynamically typed. Well, there are things you can do in JavaScript that you cannot quite easily do in Java because the type checking is going to intervene with what you're doing. Let me step back and talk about that real quick, and then we'll talk about why these differences exist. Let's, for a minute, talk about JavaScript just a little bit. In JavaScript, when you say then, and you're providing a function, we'll call this as, let's say you take a data and you call a func and on the data. Well, what can the func do? A func may return data or return a promise. This is the capability in JavaScript. In JavaScript, the function you pass to then may return data or it may return a promise. Why would you want to do this? If you return a piece of data, well then, this always returns a promise. Well, if you return a data, that data is wrapped into a promise that you're returning. If you return a promise, on the other hand, the promise that you return is returned directly. So in other words, if data is returned, then of course, it is wrapped into a promise. If promise is returned, then that is returned from the then. So in other words, this is exactly what JavaScript does. But notice how JavaScript is flexible here because of dynamic typing. In JavaScript, it doesn't matter what the type is. You can return whatever you want to return from a function. If this function returns a data, it's a data. If it's a promise, it's a promise, and JavaScript deals with it. You can't do this in Java. Why? Because the return type matters. The then accept says the return type has to be a type T. Well, if it's a completable future that you're returning, then that's going to be a little bit of a trouble. So we'll see what the trouble is, and we'll understand how to deal with it in just a few minutes. So to understand this, let's step back and talk about combine versus compose. So what does combine really do? So the combine method really is taking one completable future and combining with the result of another completable future. So to understand this, let's take a little example and play with it. So I'm going to say over here, a public, let's say, a static, we'll call this as a completable future. So this is going to take an integer value. We'll call it as create. And what does this method really do? It's going to simply say return a completable future dot supply async, and let's simply return a value of 2. We'll keep it extremely simple again. So this is going to be just returning a value of 2 from this particular example. So this is basically returning a completable future. Great. Now what I want to do here is I want to say create, but then I say combine. Well, I'm going to take two things and combine them. Let's make this a little bit more interesting. This is a silly example. I pass a number here. It's going to simply return that number. I know that's a little silly example, but it's going to run that asynchronously. So I pass a 2. Then I say create and pass a 3 to it. So what does this really do, the combine method? Well, this is going to be then combine between those two operations. So, let's see what it says. Then combine, method then combine in class cannot be applied to the given types. It needs a by function that you are going to provide in this case. All right, let's see what this is saying. Requires completable stage and then a by function after that. Great. So I'm going to say then combine. And in this case, I'm going to say I got a data on my hand. And what am I going to do with the data that I'm receiving from the then combine? Let's quickly look up this API here. So here's the then combine. So notice the then combine says I get a completable stage and a function after that. So this is going to become a create of 3, comma. Now, what does this really do for me? Notice the second argument is actually a by function, which means let's call it as result1, result1, comma, result2, and then I'm going to take those two and return result1 plus result2. So that's what I'm going to return from this call of the 2. So what does this combine do? Combine says, I have a completable future here. I have another completable future here. So this could be two different asynchronous tasks you are sending off to execute. When both of them finish, think of the combine like a join function. You're saying when both of them, I ask for pizza and I ask for drink, and when I get the pizza and the drink, I want to do something with it. What's the result of then combine? It's yet another completable future, isn't it? So then I say dot then, and I can say accept. And given a piece of data, I want to output the data at this time. Now notice, create 2 is going to return 2, as it's a really simple, trivial example. Create 3 is going to return 3, but pardon me, create 2 returns a completable future that will yield a 2. Create 3 returns a completable future that yields a 3. But when both of them resolve, this method will be executed. And when this method is executed, that will create another completable future with the value of 5. And that completable future, when it finishes, it will then come to the then accept, and the data of 5 will print out for us. And that's exactly what you saw here. So what does combine really do? So combine is something that we're not quite used to in Java. There is no equivalent of that really in the case of a stream. Well, maybe you could look at concat, if you will. So if you go to the Streams API, a concat of 2 streams, but you are waiting for one stream to finish and the other stream is going to continue. So it's really saying, take that value and move it through. In my opinion, what maybe comes really close to it is something we don't have in Java, unfortunately, right now. So I'll put it in a parenthesis. This is like the zip method. So you're really zipping through multiple streams together. We quite don't have that capability in Java, but this is really where you're getting this really nice combine method. On the other hand, What you really are looking at with the compose method is something a little bit different. So the word compose threw me off a little bit. What does compose really mean? Well, to understand compose, let's take a slight detour and come back to this in just a minute. So here's the detour. I want you to think about something a little different. Let's think about Streams API for a minute. I got a list of numbers 1 to 10, and I want to say numbers.stream, and in this case, I'm going to say .map. And what am I going to do with the map method? I'm going to say take an element, and we will call a function, we'll call it func1, and pass the element to it. Then I say for each system.out, and we will simply print it, println. So what does func1 do? Well, let's make it extremely simple. So public, let's say static int, func1 takes a number, and what it does is simply return number plus 1. A very simple example in here. Well, it printed value, let's put it times 2. It's a little easier to see it. So 1 times 2, 2 times 2, and so on. What about func itself? Well, the func1 is a 1-to-1 mapping function. What does that mean? If you give me one object, it returns one object. For example, we got wonderful people in the room. For every one of you, I can ask you, what's your first name? And every one of us has one first name. That's a 1-to-1 operation. One person, one first name, right? That's as simple as that. On the other hand, I can ask you a slightly different question. And that question is, I can ask you for all your email addresses. Some of us may have one email address. Some of us may have 2. Some of us may have 3. Some of us may have 7. But I want all your email addresses. Why? Because it's more fun to spam all the email addresses than one. So this is a one-to-many operation. So I say map given an element func2. And what does func2 do? Func2 is going to return to me not one object, but multiple objects. So in this case, I get an int square bracket. This is going to be func2. And what am I going to do here? I'm going to return number -1 and number +1. Now here's the problem. When I run through the map, what is it going to do? When I run the code, this is going to return a number -1. So sorry, new int square bracket, and then of course number -1, and then of course number +1. A little syntax over here. And what does it return? That's nasty, isn't it? What just went wrong here? Well, the problem here is func2 is a one-to-many mapping function. So in other words, if you are doing a map operation with the 1-to-1, you go from a stream of t to a stream of y. But if you do a map with one-to-many operation, so if you do a map with the one-to-many, you go from a stream of t to a stream of, I don't know, just call it a list for now, of y, which is probably not what you really wanted. Whether it's a list or an array doesn't really matter. So what if you really wanted a map of one-to-many, but what you really want to do is to start with a stream of t, but you really want to end with a stream of y? How do you really do this? Well, this is exactly where you use what is called flat map. So a flat map is useful to go from a stream to a stream when you have a one-to-many operation. So when do you use a map versus a flat map? Very easy. You have a one-to-one, use a map. When you have a one-to-many, use a flat map. So this is an operation of flat map. When you're returning a stream, you end up using a flat map operation. In fact, I'll convert this code to use a flat map in just a second to show you how that actually is going to work. So notice what I'll do here. I'll go ahead and say flat map, given an element, stream of func2, and then I'm going to pass the element e. Remember, that's returning an array. Now I'm going to call a stream on it and ask it to give us a stream from this operation. So when I execute this code, what is it going to return for us with the flat map? Let's make sure we do this right. So I'm calling the stream of, and then the func2 is returning an int stream, and on that stream I want to return a stream of objects. So let's see why that's not working at this point. This is going to be an array of data that we want to return. Looks like an int stream is not cooperating with me really well here. Arrays, let's try that, dot stream. Let's try that. Sorry, say that again. Array.stream. Arrays, as stream, yes, thank you. Arrays dot as stream. No, it's not happy. There's arrays dot stream is a function, but that's not compatible with this for incompatibility of T. Okay, let's try something a little different here. Let's go back to this code right here and say return stream.off, and in this case I'm going to say I want to return an array of values. What am I going to return as an array of values? Well, let's say in this case new object, oops, not here, new object square bracket. Let's say in this case a comma b, just a silly example just to get through this to illustrate the point about what this is really doing. So let's go ahead and close this here as an object. So there you go. So the point I was trying to make here really is, let me try this really quickly with the function. So we can say func2 of e, and maybe it just wants an object right here. Is it in stream? Yeah, probably so, but I'll convert this to a stream object for just a minute. There we go. So that's the whole point, is you really wanted to get a collection of objects, one stream of data, not a stream of stream. There was a type issue there. So basically in this case, that's the goal of a map, a flat map. Why am I even talking about flat map? What's the problem here? The problem I wanted to really mention here is when a function returns. So think about it this way. We talked about flat map real quick. So when a function returns data, we use map. When a function returns a collection, we use flat map. Well, okay. In a similar way, when a function returns data, we use then accept to transform. When a function returns a completable future, well, this is kind of like return a stream, isn't it? So if you return a data, use map. If you return a stream, you use a flat map. If you return a data, you use then accept, which we saw up here, or then apply, right? Then accept or then apply. But on the other hand, if it returns a completable future, what are you going to do? Well, now you know the rest of the story. This becomes then compose. So in other words, the then compose is much like your flat map equivalent of it. So that was a little light bulb in my head to realize the reason why you have a then compose really is when a function is returning a completable future, you want to continue passing the completable future down the chain, and you are doing a then compose for that reason. Let's look at this as a last example before we call this done. So what are we going to do with the completable future? Well, the then compose is going to compose that and forward it. So in other words, what we want is a function that in turn is going to return a completable future. To illustrate this point, let's do it the wrong way, and then we'll make it better in this example. So let's give it a try with an example right here. So let's go back to this code. This guy is returning a completable future, as you can see. So let's go to the main function, and in the main function, let's say we have another function, public static, let's say, we'll call it as completable future integer, we'll call it inc. This takes a number, and what it's doing is returns a completable future dot supply async, but it's returning the given number plus 1. So start with this for a minute. So we know what inc is doing. Okay, great. Now I go back over here and call the create method. And what does create do? Takes a 2 and returns a completable future. Well, okay, it's going to return just the 2 back to us. Then I say, then apply. And I take the data, and I'm going to say now, return increment of data. Well, then I say, then accept. And I'm going to say, given the result, go ahead and print out the result. Now, this is pretty ugly, isn't it? What's wrong with this? If you really think about it, you'll be probably surprised about this. This returns a completable future. Then this takes the result from that future, calls inc. Inc is not returning a result, but returns another completable future to say that, I might take time and work on this and get you the result later on. No, thank you. Don't install it right now. So in this case, that's for the future. So as you can see right here, it says, I'm going to return this to you in the future. Now what did I do? I returned the completable future from here. What is the then accept receive? Result now, unfortunately, is a completable future, isn't it? So what is going to be the output of this call? When I run this code, that's the completable future. Maybe not what I really wanted. So in other words, I'm saying, I want to wait for the other completable future to be finished, not for this one. So what am I going to do? I go back to this code and say .then compose, and then compose given the data, increment on the data. So I'm not using the then apply right now because the function doesn't return data, it returns a completable future. So now when I execute this code over here, you can see the result is 3. So you need to know why you want to use then apply versus you want to use then compose is when you return a data versus when you return a completable future, you want to wait on the completable future, not on just what was returned from this function. So in other words, you want to go one level below to the completable future, not at the top level. So that is basically the reason to use a completable future in there. So that becomes the reason why this is kind of like your flat map, where you are using the then compose to really extract this into a flattenet and work with the inner completable future rather than the external one. That's what you're trying to do with this. And so that gives you the compose method that you're able to use. So to summarize what we talked about the asynchrony. We talked about how threading actually is given to the asynchronous operation. We talked about why callbacks are nasty, but completable futures are really the promises in JavaScript that has been brought over to Java. It gives you the two channels, the data channel and the error channel. The data channel carries the then parts. The error channel is the exceptionally part. You can go back and forth between them, and it's a single pipeline, one set of data that carries through for you to work with the result. If you're interested in working with the code examples I wrote here and you want to download and play with it, you can find them on the downloads link on my website. You can either write it down or take a photo of it, and I'll leave this here a little bit, and you can download the code and play with it. If you have any questions, I'd be delighted to answer now or at a later time if you want to drop an email. My email address is on line number 4 as well. Hope that was useful. Thank you.